the more we thank you. The more we moved on into kind of like recent research in foundation models and data-driven aspects, we are also looking into how to model skillful interaction with deformable objects. So I won't talk about everything today, but those that are interested in learning more about what we are doing regarding deformable objects and so on, yeah, please look into my papers. So what I think for today, maybe it's interesting for people in the audience is not so much to give you kind of, solutions or pointers to how things should be done, but more discussing a little bit with everybody and having questions at the end. What are the problems that haven't been yet solved? And what I think we can also borrow maybe from other communities, such as, for example, computer vision or graphics community, to understand better how to model skillful physical interaction with the world. So the first comes, of course, to the hands, pose of hands, and then I'm saying hands because I'm really interested in looking into two hands in interaction with the world. And here I think that apart from the fact that we have been building these grasp taxonomies for quite some time and the paper is still cited very well, so just shows that people are still interested in understanding what the hands are doing. I think it is actually very interesting to see to what extent everything that has been done with modeling human pose can be used to model pose of human hands in interaction with physical objects. And I think that this comes both to human hands, but also to robot hands, understand not only how we can address grasp generation, but also understand how hands should be designed in order to be able to execute and how much also assess of the human interaction space. We addressed that long ago with various types of generative models, not in the same way as generative models are used today, but like with GPLVMs, for example. We looked into kinematics, design of different types of hands, and compare those to kind of human capability by using grasp taxonomies and so on. And we see lots of these work now coming back in order to understand better what and how can be actuated, also where the tactile feedback should be put on the hands and so on. So I think that some of the older papers in terms of understanding and getting the ideas of how maybe some of the problems can be now addressed with more data-driven approaches, I think that that's definitely something that I would suggest to everybody. And I think that what we are looking into today is more kind of like the aspect of transfer. So learning on one embodiment and then maybe transferring this knowledge to another one with some small kind of like pre-training and so on. And I think that this is one of the big challenges we have today, because if we take into account not only then the hands, but also the arms and all the available degrees of freedom and so on, regarding also that maybe we want to have multimodal feedback and so on, remains a formidable challenge. So I think that for everybody in the audience, there is still a long way to go until we have robots demonstrating some skillful interaction with the physical world. What I think is interesting is then how the work has progressed in terms of really understanding what and how can be done with tracking human hands in interaction with objects. This is just one of the examples. I think that this is MetaQuest that we are using. So having basically gaming equipment to track in real time pose of human hands and using this for teleoperation. And why teleoperation? Well, it's just one way of generating lots of data of skillful contact-based interaction with objects. So here what you're seeing is learning, or well, generating data for learning how to remove the lid from the from the bottle or the container. And the interesting thing here is if we train or use the data to train some diffusion policies for this task, we also see that with diffusion policies, we actually get models that can allow for lots of variation in terms of what the initial pose of the object is in the hand and so on. So for those that are interested more in details of this work, everything is on arXiv or in my Google Scholar, so you can give it a look. But I think that it's fantastic, as I said, that we can track human hands in interaction with objects, something that has been a problem for a really long time. Now, to move on and to think like what things can be done better, what we have done previously, and where contexts kind of come to mind. I think that it's very difficult to almost do anything without having rich tactile feedback. So we think about tasks that have to do with, shredding or cutting fruits, vegetables, or potentially preparing food in terms of like forming various types of media, granular media, maybe rice or something like that in your hand. I think that that will continue to require lots of tactile feedback, and I feel that we are just not yet there in terms of how tactile feedback is available to give us a variety of both kind of low force feedback and high force feedback. And also in combination with, as I said, challenges regarding torques that would potentially, like in the example on the right hand side, come from external forces or external interaction with the world or disturbances and things like that. Now, when it comes to contexts that can be used and utilized in interaction with deformable objects, there I see that we are still pretty far away from and how we utilized contact. But I think that we need to keep this in mind, and the important thing is why, because things like assistive dressings and so on will require us to take contact into account while keeping a stable grasp of an object and so on. So couple of things that I now would like to show as the ongoing work. We'll start with some external prehensile, external dexterity or prehensile pushing. Maybe Jens, you want to take over for the next couple of slides?
Yeah. So in this work, we are interested in how to reorient a grasped object by pushing against the environment. And the interesting thing in this work is that we allow it to push against many fixtures. So imagine that the robot can push against both the wall and the table. So this becomes discrete decisions it has to take. And usually this doesn't scale really well with the number of fixtures you can have. It's very computationally intensive and all that. But in this work, we come up with a nonlinear trajectory optimization formulation that we are pretty happy with. So if you can go to the next one. So you can check the papers for more detail, but this is the whole idea. So we want to minimize a cost function from the goal to the current position. And we have some linear dynamics that the next pose of the gripper is just like the numerical integration of the current velocity that is admissible. So we use something known as motion cones to describe that given this fixture and this friction and this grasping pose, what velocities can I execute on the object such that the object will slide in the gripper. And then we also, in this formulation, the problem is that we have these binary integer constraints. So that are the fixtures in the environment I told you about. And usually with this, you have to use expensive branch and bound solvers and all that. But we come up with quite a nice formulation. Can you go to the next slide? So here we recast the whole problem as the fixtures as probabilities, discrete probabilities. So the whole idea is that we can actually push against all fixtures all at once, which doesn't really make any sense because in the end, you always have to choose one. But how we do this then is that we add the entropy of this discrete probability distribution as a cost function. And this then forces at the optimum that the probability mass converges onto one pusher. And this really makes the problem, it's a non-linear trajectory optimization problem, but the relaxation is really nice. It works actually really well. And if you go to the next slide, we can see that the trajectories we find are physically realistic. So here you can see 3 different pushes. So with 3 different
Danica, we have
objects.
some problem with Zoom. Just 1 second. We will...
Okay, can you see or?
So the Zoom got disconnected. So we are trying to switch the computer for projection. Yeah,
Okay.
sorry about that. There's a
just let us know when we can continue. Yeah, so that's
yeah.
Okay, yeah, we can continue.
okay.
Yeah.
Yes, you can go. Yeah.
Yeah, I don't know what you heard and didn't hear, but these are some of the trajectories found by with our trajectory optimization method. And an interesting thing is this trajectory in the middle. You can see that when it grasps this squared-like object, you can see that it both in the first push, it just executes a translational push. Let's see. Yeah. And then when it goes to the next one, it actually does both rotational and translational push, which is, this was quite interesting, what it found. And numerically, we also found, if you go to the next slide, so we compared this to quite a famous paper from 2019 in hand manipulation through motion cones. And we find that our method we reach an 8 times lower cost, 20 times faster. So with our trajectory optimization formulation, so the baseline is sampling based, while ours is not. And we can see that we are much faster, get a better cost or lower cost, but it's still 20 to 30 to 40 seconds to generate one of these trajectories. So it's still not fast enough for real-time control. So these are, if you go to the final one, so these are sort of the future work if anyone are interested to talk about it. So one is to find a convex relaxation of the problem. This would probably unlock millisecond pushing or trajectory optimization. Then maybe to estimate the friction parameters while manipulating the object. Now we assume that we know these, but it would be much nicer to start off conservative, and then while manipulating, you can see that, hey, now I'm stuck. Maybe I should. The friction parameter is much higher than what I initially thought. And all of the code and the supplementary material is available online. So if you just scan this QR code or just search for probabilistic prehensile pushing, you will find everything there. So thank you for this. And in the end, if anyone has questions for my side, I will stay on.
Okay, thank you, Jens. Maybe when we go back to sequential grasping, you can also add something if there is something to add. But what I wanted to say, why is this important? Why do we want to kind of have systems like this, methods like this? So just to give you a couple of examples, what we currently do with using both LLMs and VLMs in a way for understanding scenes and dealing with language-based instructions. So no matter really what kind of robot we are using, one of the difficulties that we found is really the context-based kind of interaction with various types of objects that could occur in a scene. So if we want to remove, for example, if we want to hold a bottle opener for basically opening a bottle, this we can do again with diffusion policies. Everything has been published, so you can see details in one of our papers. But what I want to say is that holding a bottle opener versus maybe holding a spatula for moving, let's say, granular media such as rice, for example, or pasta or something like that, from A to B. I think that these are some of the challenges where we realize that then still understanding what type of grasp we can apply, just giving a parallel jaw gripper and so on, is still kind of like a challenge. And I think that the more we want to do in terms of interacting with real scenes in real environments, we will need to, apart from the fact that we want to address kind of learning of skills from rather few examples, in this case like 100 maybe or something like that, even if we deal with kind of lots of kind of contact-based manipulation and so on. So for example, here you could see we need to understand, for example, what and how hard we should grasp in order not to lose this very heavy lid and so on, and just kind of like transferring all that over different types of lids and so on. It's still, I find, kind of like an interesting challenge to work on. I'll move on in the interest of slide, but what you're seeing here is that addressing many of these tasks that require kind of like contacts where there is a tool use involved, and where, for example, diffusion policy has learned this kind of like shaking based removal. There are lots of external forces acting on the tool, and I think that the contact really needs to, or the contacts that we applied on the object need to really compensate for quite big changes in forces. So I think that that's quite interesting to work on. Now I'll move on a little bit to tell you what we are working on right now. Of course, we are very much interested in looking into the development of dexterous hands and understand how a hand can grasp not one, but several objects, 2 or 3 at the same time. Again, not a new problem. People have been looking into that in 2 different ways. So either a simultaneous grasping, something like applying a Pavel grasp to simultaneously on the number of objects, or looking into sequential grasping. So how we can plan and use the dexterity in the hand, and then through kind of contact-based ability estimation and so on, plan to grasp various types of objects. And of course, this is also based on some of the older work that we have again done related to the taxonomy, looking into how we can use so-called opposition space and find hence subspaces for applying these oppositional forces in order to satisfy stable grasping conditions. Again, this is pretty new work. It's on arXiv. If you want to give it a look, we compare it also to the baseline. So multi-grasping, as I said, where in that particular work, maybe object-object interactions are more important. Just a couple of examples here to show you how building on then, again, diffusion-based work that we have done before, we can generate a couple of examples of grasping objects and then test those through shaking. And here on the right hand side, you see a comparison to the multi-grasp approach. So again, we only have 1 publication on this. We will continue to work on this, and then we'll see how far we can come. Jens, do you want to add anything on that work, or?
No, not really. That was
okay,
really
good.
everything.
Yeah, okay, yeah. So just said we just kind of like started. So but so why I think that all of these things are important when it comes to integrating then tactile multimodal feedback with dexterity, because many of the things that we would like robots to interact with, from kind of like different types of connectors that actually need to be pulled or pushed in with high forces, even if it's kind of like a single degree of freedom, you push it up, down, or you pull it up. Or if you would like to interact with very fragile objects, maybe raw egg or something like that, or even food, vegetables, tomatoes, and things like that. I think that having all this variety and understanding how then tactile feedback can be utilized in order to apply well, stable grasps, but also some form of let's say post-action. I will show you what I mean by post-action. So after applying kind of like grasp, we need to understand what and how then well, what to use it for in a way. So when it comes to connectors, maybe it's about, you know, pulling it out, so to speak. But I think that the interesting things will come from, let's say, okay, lifting an egg has been seen. I think that interacting with fruits and vegetables is really interesting, because if you would like to have robots that, you know, do some agricultural tasks and so on, what I meant by post-action is really pulling it from the rest, kind of like of the either the tree or the branch. And I think that this is interesting because it just shows how difficult it is really to first detect one of the kind of like grapes and then pull it without destroying the rest of the plant and so on. So I think that tactile feedback and then context-rich manipulation will continue to be kind of like an interesting problem. Now, about the data and learning from humans, I think that there is still a lot to wish. Why? Because even if we can teleoperate robots in one direction in a way, and I showed you how gaming equipment can be in a way used to generate the data or teleoperate hands, humans don't get the feedback in terms when contact occurs and so on. So it's very difficult kind of like to generate good training data. What we have looked into, whether vibration can be used to give humans some ability to address or really feel the contact. But I would say it's still rather limited. So having kind of maybe gloves or something else that would give feedback to the human when in a way the contact occurs would be really kind of like helpful. So I'll stop there. I'll just have this slide kind of on and I'll stop share mostly for the interest, and maybe Jens, if you want to show yourself, so if there are any questions, we can address them. I think this was about 20 minutes, yeah. Thank you.
Are there any questions from audience?
Mm?
Okay, can you use that microphone? Can you use that microphone?
Yeah, I was just wondering, how does this generalize across degrees of freedom? So you have, let's say, 2 fingers, 5 fingers. How do you work with them?
You mean the pose of the grasp, or are you asking me or for the Jens, for the work that Jens presented?
For you. The pose of the
Yeah,
grasp.
right. So what we looked into previously was how we can find some form of a subspace. And we did this with GPLVMs long ago. So looked into how we can find a low dimensional subspace of different poses. And of course, I'm not saying that I can generate kind of dexterous grasp on a 2-fingered hand, but what we looked into is whether we can compare what part of the subspace of all grasps that originally were generated by human grasping can a certain hand design cover. There is a transaction paper on that where we suggest some measures for kind of assessing the anthropomorphic capability of robotic hands. So that was how we did it. Looking into what I would do, really, it depends a little bit on the kinematics of the hand. I mean, if I have something like an all shadow hand with 3 fingers, and then something that is, that is not anthropomorphic and so on, I suppose that today I would just kind of generate examples in a data-driven or whatever manner for that particular hand.
Any other questions? Hi, thank you for the great talk. I have a question for Jen.
Yeah. Yeah.
I was kind of looking over the model for the pushing the mixed interior linear programming model. I was just wondering if there are any like additional complexities that you can think of if that model is to be applied for non-prehensile interactive manipulation. So where you're not like directly manipulating the object, but you're sort of like pushing it from just like the rigid body itself.
What I missed the last thing, pushing from.
Oh, if you're not like actually like manipulating the object, but more so using some sort of like a robot pushing. So like a mobile robot that pushes an object or something.
Ah, yeah. Good question. Well, the theory we based ours on is called motion cones, and that defines pushing as if I have frictional contact with the object, which velocities are then admissible for pushing without the gripper sliding on the object. So one of the assumptions you have is that you will, once you have contact, you will have contact. So if you continue sticking and breaking contact, I think that will be a problem with the mobile manipulator, maybe. But otherwise, I don't really think it's also a lower dimensional problem, because if you just have forward and backward and steering, it should be kind of doable, maybe. But it's a great question. I haven't thought about that.
Thank you. That makes sense with the contact breaking.
Yeah.
Yeah, I was thinking if you're just using external pushers, I guess like standing it.
Yeah, then it should work.
Thank you.
If you try it, let me know.
Okay, yeah. Thanks again for the insightful discussion. Let's move on to the next speaker, Paarth from PRI, on his talk on scaling Dexterous manipulation with large behavior model. Let's welcome to his talk. Sorry, it's a little bit dark, but okay. So let me try to find HDMI cable. Do I have HDMI cable? Okay. Or like a type C. I think we have the adapter. We do a search. This one.
I think I have a.
Nice. We are getting the light again. Okay. We're drawing the zoom.
Oh yeah, more in the Zoom.
Okay. Oh yes, great. Share the screen. Oh, sorry. Are you able to share a screen?
Is it? We good?
Yes, we are good.
Let me know if I should start.
Okay, yeah, feel free to get started. Yes.
Nice. Cool. So, hey everybody, my name's Paarth. I'm a research scientist at TRI. And today I'm going to talk about scaling dexterous manipulation with large behavior models. And so currently, like, I just want to start with like where robot deployment is in the real world right now, is that they're very limited tasks and they're confined to like very specific areas.
So like on the left, we have like Spot doing like robot surveillance in like oil rigs and nuclear facilities. And that's like, it's awesome to see these robots in the real world, but they're like very limited here currently. On the right, we have Waymo, which is kind of has a much bigger depth of like deployment. They're like out in the real world in like on the streets and stuff. You can order them depending on where you live. But once again, it's like very limited, and these aren't really a part of our like daily like life right now. And that's kind of where we want robots to be for most of us at least. And so if we narrow the scope a little bit even more, so manipulation is even like way further from deployment. So they're mostly like logistics. So Dexterity doing stuff in like logistics factories, a Toyota factory where they're like confined to like work cells and like very like specific types of movement. So they're not very dexterous. They're not very like, they don't have much common sense. They can't deal with things that are out of distribution. And we kind of need that when we're out in the real world. And so specifically, like, what do we want our robots to do? We kind of want our robots to actually like be a part of our daily lives. So like folding clothes, interacting with different objects in our households, like cutting, doing kitchen tasks, whisking, using tools, even like really precise tasks like soldering, putting things away in the dishwasher. You really need to have some sort of like precision and like being able to like understand what the real world is giving you and how to be able to adapt on the fly. And so with foundation models, we're kind of getting close to that, right? So it's like we started off and there's this entire field kind of looking at like poking at generalization from the perspective of data. So right, we have like RT2 from a few years ago where they're kind of understanding and poking at general like how general are our robots. OpenVLA, which I'm saying in playwright, but I'll start again. But like OpenVLA, which was done at TRI as well. See if I can. So yeah, RT2, which is kind of like this more general like robot. And they're not very dexterous. They're kind of doing pick and place tasks, and they're kind of poking at a specific type of generalization. But I think for robots to be like useful in the real world, you need common sense and dexterity. And I think we're starting to get there. There's been a very big switch over the past like year or so, where a lot of these foundation models are like starting to like actually show a lot of like really awesome capabilities. And so really quick, what is dexterity? Dexterity is like one of the most like overloaded like terms in like manipulation and definitely in like robotics as well. So my colleagues and I have a bunch of qualities that we're looking for when we're talking about dexterous tasks. So one natural one is like, okay, it needs to make a lot of contact before. That's fine. Very natural one. Part of that is like tool use. It needs to be able to understand how to like adapt to like different tools on the fly when they're available. And so that kind of comes with the contact territory. Two is like multi-arm coordination. So on the right, we kind of have like t-shirt folding, which we've shown a bunch of different times, but like the robot arms need to actually coordinate with each other and like work together to actually achieve this task. Another thing that I think we're looking for is like precision. So like with a lot of these tasks, we also want them to be very precise. We don't want them to just kind of be like moving around a bunch and like not actually being able to do like very natural things. So like unlocking a ziplock, things like that. And we'll get to a couple examples later. And this is not necessarily part of dexterity, but I kind of throw long horizon in there just because I think you kind of need all of these like qualities to also be like along for the ride for the entire like part of your trajectory. So you need to be able to like switch, do something that's like not as like dexterous and not as precise, but then also go back to be precise. And that's part of like long horizon capabilities. And so today I'm going to talk about like how like dexterous abilities scale with large behavior models. And specifically what I'm going to talk about is like some of the work we've been doing at TRI studying dexterous capabilities, how we're studying them, what sort of generalizations we see, and maybe like convince some of y'all why a data-centric approach to dexterity might be like the way forward. Cool. So just as a backdrop, this is one of the tasks we've been studying a lot at TRI, and it involves quite a lot of like different contact making and breaking with a bunch of like different like contexts of apples. It's making tools. It's very long horizon. And this is just a rollout of like what we're seeing while we're like actually evaluating some of our policies. And it doesn't always work, but like we're getting there and we're getting really close. And so studying dexterity is like important because this is something you might actually see and like do and ask a robot to do eventually. And we're not the only ones studying dexterity from the perspective of foundation models. You know, you have Pi doing their thing, folding clothes, lots of different dexterous tasks actually that they had with Pi 0. Gemini Robotics doing like origami folding. So very precise, very dexterous as well. And so just want to note that like we're not the only ones doing this, and there's a lot of work going on in the field around it. And so, yeah, how do we approach dexterity from like a data first perspective? And so a lot of this is going to be like very like common knowledge to some of y'all, but for the rest, I'm just going to briefly overview like what goes into like a foundation model. And why it may be like a really like nice recipe for scaling dexterity. So this is just a random architecture I chose. This is Palejama. And the way it works is, one, you just get a bunch of language, and two, you get a bunch of visual data, and three, well, that's all it is. And so really, it's like a really nice recipe. You just need a bunch of data, and you supervise your language. And sure, there's some extra like things that go on top of that, but like that's really like the basic formula, and it goes really far. As you can see, I think most of us use ChatGPT or versions of this in our like daily life. But what goes into like a robot foundation model? Well, really all you need to do is add robot data and supervise their actions. So you take this like pre-trained recipe and you add robot data, and boom, you kind of have a robot foundation model. So very simple, scalable recipe. And yeah, so you have different types of robot data. You may have extra like types of like vision data, so like Ego 4D, different language, VQA data, as you like start to get more like in depth, and then also like sim data as well. If you like want to like start and like study some of these like behaviors in sim. And so this is just like the entire recipe for foundation models for robotics. And so just looking at this from a like robotics perspective, what does that really mean? So really it's just a visual motor foundation model. And so all you do is take your observations, so your cameras, you take your like robot state, put that through one model. So robot state, vision encoder, get a language encoder, and throw an action decoder on top. So that action decoder is also technically may come for free as well. And you supervise your actions. And there's a lot of different formulations of this. One, you can have an autoregressive formulation, so like OpenVLA or RT2. All you do is take your discrete tokens, supervising that. There's diffusion, which is a more continuous like version of that. And you have flow matching, which is like a more like nuanced version of like diffusion, and a more general formulation. And so that's really all there is to it. You can get fancy, you can add different things, like you can make your vision and like language encoder one big like VLM, and that kind of like gets you kind of a lot of your like common sense knowledge. But today we're going to focus on just the diffusion aspect, not because we don't have these models. We have a lot of different like large models at TRI, so we have VLMs with like flow matching, we have all different variants, but we just spent a lot more time actually digging in and studying a lot of like these more basic like diffusion transformer, just pure diffusion models. And so just as a note, this is like our like architecture that we're currently studying and talking about today. So really it just concatenate a bunch of your observations, concatenate your diffusion time step, noise your action, and denoise your actions. It's very simple. We're using a VIT for like images, we're using a VIT for language, and there's nothing super fancy going on here, but I think that doesn't really matter in terms of the like architecture for like studying dexterity right now. And digging in a little bit deeper, the thing that I think does matter is actually the data mixture. So overall, in terms of number of datagrams, we have this like OXC pre-training, different types of like embodiments, and we call our like mixes TRI ramen, just for natural reasons. So we have real data, we have sim data, we have GUMI data, and when we're actually like training these data, we batch balance them in order to like look for different qualities. It's not necessarily the most optimal way to batch balance, but like yeah, there's a whole like different science. There's a whole science to that. And so that's kind of what we're doing, that we're upweighting our like real data just because we think it's a lot more high quality. And we're like looking at like things like sims so that we can like maybe evaluate these things in a much more thorough manner. So just digging in a little bit deeper is like a little gallery of some of the skills, but like we're going for a very diverse set of skill sets. So we have 500 different skills. It's around 500-ish hours as of a few days ago. It's a mixture of sim and real. And it's a mixture of long and short horizon tasks. But like I said, the main thing we want to really like focus on is like the high quality data. So I think high quality data is like one of the most important things for these foundation models. Cool. So that's our like general recipe. So how do we study large behavior models, foundation models for robotics? So the training regimen is like pretty straightforward. This is kind of following what most people kind of do. Just here's a base model, take your TRI ramen or like base like amount of data. We take a pre-trained generalist. Then when we, for an unseen task, we fine tune on new data. And that is like our entire like recipe. It's supervised fine tuning, nothing fancy at all right now, but it gets you really far, as we can see, or as we'll see eventually. And so going back to the data mixture, one thing you'll note is that the sim data is like a very small amount of our total amount of data. And how do we use sim? And I just want to note that we don't use sim for like data generation and try to use it to like actually bootstrap and give ourselves more different types of like qualities of like motions. So really what we're doing is sim and real co-training in order to scale the evaluation. And what that really looks like is using using our simulator, LVM eval, which is based off of Drake, and just like breaking that up into a couple different variations of scenarios and really digging in deep to understand what sort of qualities we're seeing when we are scaling these foundation models. So one of the things that like I want to note is that like they're very contact rich, like scenarios. There's a lot of bimanual coordination. Not everything is technically bimanual, but most of the tasks are bimanual. There's scenarios that are specifically poking at like language steerability because that's an important part of a sort of foundation model. And once again, mix of short and long horizon skills across like different types of scenarios. And one of the important things about evaluating in sim is to be able to like actually get a sort of signal in the real world. And what that means is that like in the real world, almost everything you evaluate on is some sort of out of distribution. Like there's some sort of distribution shift involved with that. And so with sim, we're also able to like capture a lot of these out of distribution scenarios. So like we have different distribution condition or initial conditions, lighting, novel camera intrinsics and extrinsics, backgrounds, and like object textures. And so we're using a lot of these things while we're actually evaluating to like understand where these like actual policies break down, where they may be useful, and what sort of distribution shifts they're like actually generalizing to. And we also have like very, very like sharp, like we can change them on the fly. Some of them are like quite like funky, like purple bananas and stuff like that. But yeah. And a closer look at some of the tasks just to like get people like situated. So like some of these are like a little bit more long horizon. You're like passing something over, putting it on like a table. Some of them are very short horizon, like single arm, like I said. And that's just kind of like just show you the flavor of like tasks we're looking to evaluate on. And just to like, we're not looking at the Dexterous tasks yet, but just to like get a gauge of where we're at, just fine tuning to like new sim tasks in sim is like also like very like useful. And just want to say that we're only slightly better with distribution shift. But like I said, when we're actually evaluating these things, I think we're only slightly better without distribution shift. But I think when we're actually evaluating these things, we really want this distribution shift to be on because that just kind of like more captures what we're seeing in the real world. And so with distribution shift, these foundation models are like with confidence intervals much better than the actual like single task from scratch policies. Great. So those are some like the like simple like easy tasks. So poking at like dexterity and simulation is just kind of what this talk is about. We have a couple different tasks that are a little bit more long horizon. So like picking up like objects, putting them in like containers and like pouring them. So it's a little bit more like dexterous. There's some more like actual like types of motion involved rather than just more pick and place. And these kind of test some of the more like long horizon capabilities and like dexterous capabilities. And I'll just let this one finish because it's like kind of fun to watch sometimes. But this is all super possible because like the contact physics of Drake and stuff allow us to like do super interesting things with these tasks. And then one more just hope it plays. Oh, maybe not. Sorry about that. All right, so fine tuning to like some of the just looking at some of this dexterous tasks and like fine tuning. So what we're seeing is that like in general, like the fine tuning results they are better, but there's a lot of nuance here. You expect them to be like quite a bit better in sim, but with distribution shift, they're only slightly better. And one of the like hypotheses that we have is that there's not that much sim data. It's really hard to like bridge a lot of sim data and bridge real to sim data to get that sort of like signal. And so we've been like focusing and like thinking about things like how do we actually use sim in a more like unified manner. And so although we do see some of these like these improvements, really we're going to like step into the real world and really study dexterity in the real world. And first task we're going to look at is this like kitchen task where really it's very long horizon and yeah, so it's really long horizon, but it's more about the like coordination between the arms. So this is one of the fine-tuned like policies, and you'll see that like it's able to like do a lot of like different things all at once. And I'll get into like some of the results in a bit, but this is also just fun to watch. It's like even though it's like quite you lose a lot of the images when you're like doing some of those tasks, like opening things. It's still able to successfully do that. It's pretty reactive. Yeah. Yeah. But yeah, so that's one of the tasks where we're like really seeing that there's a lot of like effect of like using a foundation model. Cool. So next task. So that's something that like when we're looking back at our original points of like dexterity, that's the long horizon, like coordination. This one's like a task that's like essentially putting a bike rotor on a bike. And this one is like just requires a lot of precision. And so like just seeing how it like is able to like coordinate and actually like complete this task is really impressive. And by the way, I just want to note, these are all like 200 to 300 demos. They're not that many demos with respect to like the amount of like demos I've seen in like other types of what's it called, like foundation model papers. Some of them have 2,000 to 3,000 depending on the type of task. But these are able to like really like do quite well with a few number of demonstrations. And I really like how it like stabilizes it and be able to do that. And then finally, there's also some tool use. It's clearly able to like understand how to use different types of tools in the environment. And I mean, it's naturally taught, but I think we're naturally going to see as some of these things scale, how they'll transfer over to new skills eventually. Yeah, this one's super fun to watch. Yeah. Cool. And then finally, this is like one of the Apple tasks that I was showing earlier, and we're going to just see how it's like able to like use many different types of tools all at once. So you start off by like pouring the apple, which itself is like quite difficult. And pretty much in this scenario, like everything is out of distribution from the perspective of like, you can't have the same apple every time, you know, like there's apples that come with different shapes and sizes, and like it's still able to generalize to all types of like many different types of apples. It's able to like unsheath this knife, which is like great. But then most importantly, it's doing this really fine, precise like cutting maneuver. And this is super difficult. Flipping this apple is insanely hard. Like it requires a lot of coordination and a lot of like fine-grained like motion. Setting everything up to like cut this task. I mean, this is one of the most dexterous tasks I've seen a robot do, to be honest. A little biased. So grabbing to clean the knife, and with this one, one of the nice things that you'll see, actually, it was really cool that we caught this on camera, is that it failed. The like napkin dropped, but the robot didn't care. It's gonna go back and fix itself. That was not taught. And then finally, the knife is going to, you know, sheath itself, which is a really hard, precise task. That's like insanely hard, clearly. And so those are the type of capabilities we can do with some of these like foundation models with very few demonstrations. And so what does that look like in the real world? So just generally what this looks like is, okay, you're going to see this and you're say like, okay, it's like not helping that much, but I think that's actually not the full story. And you'll see why, but I think you'll see that in general, it is helping. The success rates are high across most of the tasks. And we're doing 50 rollouts of each of these tasks. So it's like quite a large number of rollouts. It's a lot of like work. We've actually done way more than 50 at like this point. And then we have a lot more real world data, which is also why you're seeing a lot of this like much bigger like delta between like the sim and real tasks. I think that's one of the main roles that or one of the main things we're seeing that like shows us this like slight difference in like performance increase. But I always want to point out that success rate isn't everything. So like we looked at like dense metrics and stuff when we've started looking at dense metrics. Actually, we haven't for a while. And one of the things that like is like very apparent to us is that when you look at task completion, these LVMs are better. So like, even if something is deemed a success, which like we have very hard criteria for success and like failure, these things are doing better overall. And I think one of the most like, I'll show you an image right after this that shows that like just makes it very apparent. But these things are doing much better. And so why should we use an LVM to like fine tune tasks? Why should we use these to study dexterity? And this is the image I'm talking about. Essentially, the single task on the left, like its failures are like very apparent. On the right, these are failures. Like there's a lot of things that are considered failures, but it's very clear that this thing is doing much better. This thing gets almost all the way through. It's much more like smooth, and it's like much more closer. It's a much higher level of success than like any of the like single task policies. And if we dig in deeper, when we look at the failures of some of these policies, it's actually even more apparent. It's like these things are more reactive, and the worst rollouts for like the single task are like just catastrophically bad, where it can't do the task at all. It's just like open looping behavior. On the right, even though it's failing, it like will go through and like actually like actively like try to like fail gracefully. They'll try to like redo the task. And these things are just generally like a lot more like have a lot more common sense. They're like able to deal with different like out of distribution shifts. I think that like points to like using like having like data as like a backbone just like makes a lot of sense to me. And the other thing is that when we look at like scaling with data, I think this is another really important plot. Is once again looking at the distribution shift plots. These are like the hard tasks in sim, but with like 50% of the data, we're doing better than 100 tasks, 100% of the data with like 100% of our like single tasks, 100% of our data from the single task perspective. I think that's like a really powerful statement. Essentially, you can learn more. What you can learn more efficiently. So with fewer demonstrations, you're getting the same like level of like task success rate. And we're seeing this in the real world too. So essentially, we've like studied like some of these scaling laws. This is for one of the specific tasks, this breakfast table. Go with like 50% of the data were much better than the 100% data from like the single task perspective. I think just from that perspective, scaling these things seems to make a lot of sense. And so just coming back to like this initial like task, like the Apple task, how good are we really? And I'm not saying we've like solved dexterity or anything, or we solved manipulation, but we're getting really close. And it's like fun to see like a lot of our failures are like very common sense like failures, and it's able to like sometimes like correct itself. And I think that's like really important and like speaks to like a future where like having these pre-trained models is very useful. And if anything, we can like look at maybe some like DeepSeek, where something like you only need 10 to 15% of your like performance to actually start to get better. And I think even with just like common sense knowledge like this, it's really exciting to say like, hey, like we're doing a lot better than we were before, and we're doing this on like a bunch of really hard tasks. Cool. So like just taking a step back, what I talked about today is kind of like dexterity from a data first perspective and why it might be like super useful. So I mean, like I said, we're like very robust at distribution shift. We studied that pretty like a lot in sim. We studied that in the real world because technically everything is a distribution shift. There's more graceful failures. So like the like bike rotor task, where we're kind of like showing that it can fail and like it can kind of come back into distribution. Same thing with like some of these Apple tasks, where like even when it does like miss the grasp, it will go back and it will like be more reactive. And from the scaling plots, you can show that it's like actually learning faster, which is really important. So with fewer amount of data, you can actually get to like very good levels of performance. And as we increase the amount of data, I suspect those like scaling plots will also start to like change and like look dramatically different. And so just in general, like these pre-trained models are like out of the box generalists. Right now, like zero shot, a lot of the times they don't do that well, but like they're really robust specialists. So when you start fine-tuning, when you start looking at like using these tasks for like other like in different domains and like fine-tuning them, they're just a lot better. And I think that is like a really like awesome place to be in, because we can learn things really fast and things are moving really great, and like from the perspective of like manipulation, and you know, these are like real world tasks that you might want to like actually do in real. And I'm just gonna kind of leave you with this, because this one's, if this one works, I found that all the like square videos they had didn't seem to have worked. All right, but it was just kind of a video of like, if you don't give the like policy language like any sort of like language commands, it'll just start to like really like interact with the environment and do common sense things. So like, it'll pick up like a broom, it'll pick up like oranges, kind of like it would like I'd seen them before. Like I said, I think when you think long term about that, having common sense knowledge and how to like interact with objects rather than like interacting from scratch is like a really great place to be at. And I think we're just gonna like get a lot better from there. Yeah, cool. Thanks.
Thank you again for Paarth's great talk. Are there any questions from the audience?
Great talk. It's very interesting to know. Hello, thanks for the great talk. Very impressive result. Just curious, when you're using for the Apple tracking demo, you only need a few demonstrations. How exactly is a few?
Yeah, sure. Sorry. Few is like in our world, like, okay, it's different. It's like 240, 250. But I think that's like in the grand scheme of like when you compare it to some of the other foundation model papers, like Pi doesn't explicitly say how many demonstrations they were using with some of the like their tasks, but like with like Gemini, some of them was like 2,000 to 3,000, I believe. And so like I think few when it comes to like the field in terms of doing these dexterous tasks.
Well, makes sense. To follow up on that, so I assume those couple hundred demonstrations are full demonstration, right, from beginning to the end.
Yep.
As you test the rollouts, you will see maybe certain part of the task is more likely to fail. Do you have a more efficient way to recover from those type of failures rather than reflect the whole failure?
No, so like in the past, what we've done, I think, so for example, like the task where we were like unzipping like the ziplock and like doing that, a lot of times we'd like kind of induce failures while we were doing that to like then like show some sort of like recovery. I think that's maybe not the like right way, but like that's what we've done in the past. I haven't seen too much stuff out there in terms of like how to like actually actively like gather demonstrations yet that are like from failure to like success to like be able to like bootstrap off of that. So right now we just don't have a very good like formal way of doing that.
Good enough. Thank you very much.
Yeah.
Thanks for a good presentation. I'm really impressed. I have 4 questions, and some must be very basic. Anyway, all the questions are based on my curiosity. First question is, are actions joint position?
We use end effector space for our actions. So SE3 end effector position.
End effector pose?
Yep.
Okay. The second question is the resources needed to train those models. For example, I have A6000 in our lab. How much A6000 do I need to train your models?
That's a great question. This is coming from an industry perspective, but yeah, so I think fine tuning these models, you could do it on A6000, train them from scratch with the amount of data we have, probably like 8 for like 4 days, 8 to like 16. Yeah.
Oh, for the A16 with how many A16?
No, sorry, probably 8 to like 16
days.
Oh no, so in terms of days, probably like 4 to like 6, but you probably need like at least 8 to like scale this up in terms of batch size and stuff like that.
Okay, thanks. The third question is, does it have a function to avoid collision?
Okay, so that's actually a great question. So the controller underneath is a differential inverse kinematics controller, and we actually we have collision modeling for the table and the other arms, but not the actual like objects in the seat itself. So that when we're demonstrating, we will absolutely not hit the table and we will not hit the arms. And so that's like another really nice thing where it's a very model-based controller underneath that's like just making sure everything's smooth. So they won't collide with the arms.
Last question is it robust to camera position?
To some degree, yeah. I mean, we've like done some tests with like moving camera around, but like certainly I think one of the most like devastating things is like actually hitting your camera in the lab and being like, oh yeah, this is rough. But I think if I were to hypothesize, I think when you move to a mobile base, you'll have less of those problems just because you're like naturally moving your camera around during demonstrations. And I think that's probably like just a like defect of like just having fixed scene cameras.
Okay, Paarth, fantastic presentation. I have a question about if you are giving a new task, you also have some specific categorizations on what range of the issue configuration you want the policy to generate. So what are the specific steps and how long does it take to actually get to the final policy you want? Like you have to set up the large behavior model, digital twin, multiple iteration of data collection. So how does the whole life cycle of a policy work?
Yeah, that's a great question. So I think so we have a lot of at TRI we have a lot of like robot demonstrators. So like we're not the ones collecting data, and they have like a really good like internal knowledge of that. So they have just like by like virtue of like them being there for a year, 2 years sometimes, they've had a lot of like understanding of like what policies work and how to set up a scene so that they're like successful with their data gathering. And so usually it's like 1 or 2, or it's usually like 2 rounds of like for like these dexterous tasks, like 2 rounds of like iterations being like, hey, this didn't work, why didn't it work? So you'll have like maybe 50 demonstrations, train a policy, or maybe it doesn't work. Maybe it has these like natural failure cases, do it the second round. And usually by the second round, it's like pretty well done. Like they know exactly what sort of like behaviors they can do to like demonstrate that'll make it successful.
Hi, yeah, cool. So I just know that the diffusion policy, they use like 2 steps or frames of the observation horizon.
Yep.
And I guess that limits like a lot of how much long horizon stuff you can do. So are you limited by that? Or like I see that like it's not repeating the same state with encounters somehow.
Yeah, that's definitely a defect of certain types of long horizons. So you can imagine like a mobile base where like I'm doing something on this side and I'm turning, and for sure you would have no understanding and like you would not have a memory of some of the tasks you've done before. I think, like I said, coming back to like the data collectors and like how we're setting up our tasks, we're very well aware of that. And so like we kind of have to take that into a constraint, and like the robot teachers are very well like aware of like how to like demonstrate so that doesn't happen. But we do have formulations hopefully where we're pushing on the context length to like make sure these types of like failures don't happen.
No, awesome presentation. So I have a question. So for a model, does it also handle singularity joint limits, or is actually handled by the differential IQ controller? But I think controller is really hard for it to handle. We need a planning layer somehow to actually, if the action really involves singularity, or bypass it. Another question is, for your model, does it also output like null space poster, or is actually also handled by the differential IQ control? Thank you.
Yep. So everything in terms of like dealing with null space, dealing with like the actual collision and stuff is handled on the controller side. You're right in that like it may not necessarily like be like right to do that, but I think based on our demonstrations, we don't really hit those like postures very often because we're like demonstrating in a way that like that doesn't happen. But like if you're doing cross embodiment, naturally you could maybe see something like that happening, and maybe like the controller needs to be a little bit smarter about how to like handle those constraints, and maybe the controller needs some sort of horizon too.
Thank you. Due to the time constraint, let's take the last questions. Great talk.
I want to better understand the scale that you collect at TRL. For example, how many hours of data could you collect per day, and what's the size of the pre-training data set? And you show a lot of curves, and I see clear trend that large behavior model clearly outperforms the baseline. But the success rate is on some tests 20%, 30%, or 50%, 60%. How many more hours of data do you need to make it 99?
Yeah. So to your first question, I don't think I can talk about like specific numbers in terms of hours per day. That's just by proprietary information. I had a slide to show for this set of models, we had around 500 hours in terms of like TRI data. We've had more since then. But I think coming back to your second question, how many more hours would it take to like get that success rate up? That's like a generally great question for the field, and it's very task dependent, right? It's like the tasks I showed today were like specifically focusing on these really dexterous tasks that have low success rates, but we have a lot of like pick and place tasks and stuff that are like very much in like the 95, 96% percentile. And I think in terms of that, like you wouldn't need that much data, but for like the 20 to 40 to like get that to 90, that's an open question that I don't have the answer to, unfortunately.
Hey, great. Yeah, let's thanks again for Paarth's great talk. Let's welcome Professor Kris Hauser for his talk titled "New Models for Bridging Contact-Rich Planning and Perception."
So we have the HDMI cover. Oh, yeah, I have to say, hey, I'm trying to talk. Okay. Okay. Yeah, take our time. Okay. Yeah. There sound like a technology challenge. Like I'm also I connected to the Zoom.
Three computers, 4 computers here connected to the same phone.
Yeah.
Absolutely. And then I have to share my screen.
Yes.
So I understand.
We'll add you as a co-host to make things easier.
Well, the Wi-Fi is not offering. Let me at least do my introduction while Zoom spins up.
Oh, it's working.
Oh, there we go.
There may be a
Optimize. You need to be able to.
How about that?
Yeah, that works.
All right. Okay. That's okay. Well, thanks everyone. My name is Kris Hauser from the University of Illinois. I'm glad to be here and thank you for the workshop organizers for inviting me. I am also Xiaoshang's advisor. I did not invite myself to this workshop. So I think he's trying to kiss my ass. But actually, I'm going to speak a lot about his great work. So I'm actually going to be kissing his ass today. So I'd like to talk to you about new models for bridging contact bridge planning and perception. Another subtitle for this talk is going to be AKA modeling and reasoning about stuff. And so I'm going to talk about different ways of modeling worlds that I think have the promise to tackle some of these problems we're interested in with contact bridge manipulation. So I'd like to, in contrast to the previous talk, I'd like to kind of call back to the older and more, I guess, blissful days where we used to think about the world as a bunch of rigid objects. We have all sorts of great models for rigid objects, geometry models, contact models, etc. And these worlds have been great for doing a lot of tasks with robots. They are very explainable. We can do mapping, simulation, planning, and they also have high precision in many cases. However, they lack flexibility. They don't really do a great job of physics estimation. They're also sensitive to perception inputs. In contrast, we have a lot of recent effort in policy learning-based approaches, both end-to-end learning as well as imitation learning. And they allow you to think about the system with much less complexity. You have on the inputs sensors, and you have the outputs, either torques or some kind of low-level controller. They're fast to bootstrap with data, fast-ish. I mean, you throw data at it and they'll start behaving rather than having to wait for months or years for your system to become integrated if you take a more classical approach. And they also allow us for task level scaling. However, we lack a bunch of the great things that made these rigid object worlds so useful for so many decades in robotics. They're not very explainable. Memory is a bit hard to kind of understand these methods in terms of long-term memory. Also customizing these post-training, you can do fine-tuning, but how much data do you actually need for those new tasks? And they're also sensitive to the distribution in which they're trained. And I'd like to say that these cognitive representations here, these are indeed cognitive representations. One is more model-based, the other one is more policy-focused, but they lack a certain something that biological organisms like humans possess. I'm going to show you this cute little video here of this Chihuahua. So this Chihuahua, I guess, they shiver and they're cold, and he's standing on this soft sofa and finds this, this blanket thrown at him, and he figures out how to manipulate the blanket, on his first a couple tries, he's kind of kicking around in it, feeling how it acts. But eventually he gets to a nice warm spot underneath the blanket. By the way, my dogs do the same exact thing. Then they end up ripping the blankets off the bedroom. So it's really infuriating. But you can see that this is a really amazing behavior. And if our robots could do something like this, we'd be very, very happy. But I think we need new representations that enable this kind of behavior.
So why do we need this kind of behavior? Well, there are lots of applications that demand us thinking about the world as a bunch of stuff rather than thinking about modeling the world explicitly or having a fixed camera angle that looks at a certain tabletop. So agricultural applications, household applications, medical applications all require dealing with deformable things like plants, bed sheets, and people. And then for outdoor applications, we have to deal with terrain, whether we're doing scientific exploration, whether we're driving across terrain and driving through bushes or excavating things in construction sites. So I'd like to argue that an ideal cognitive representation of worlds is neither a scene graph of rigid objects nor a bunch of pixels. I think we need a few things, or we'd like to have a few things in these ideal cognitive representations, which they just don't exist yet, but I'd love to see these. I, by the way, have a background of motion planning, and I've been wanting these types of things so long, for so many decades, and I think we're getting closer to having the tools to be able to produce these kinds of representations. So we want to be able to represent fully deformable 3D worlds. So this is thinking about the worlds as stuff. We want these models to be adaptive to the observed behavior. We should be able to put our robots into a padded room, have them play around with things, and then learn how everything behaves in that room, and at least asymptotic. We'd also like to integrate some of these nice tactile sensors that Danica was talking about earlier. We'd like to be able to integrate vision and touch, and maybe even other modalities too, like audio and smell and all sorts of other things. We'd like to be able to deal with heterogeneous materials. You know, humans are heterogeneous. The chairs that you're sitting on, they're all heterogeneous. We'd like to be able to deal with all of those. And you know, although I think we'd like to be able to learn from scratch by interaction, we also can leverage potentially background knowledge, priors, foundation models of how this stuff behaves, but then adapt later after you start interacting with it. Oops, something happened here. Oh, that was interesting. We'd like to be able to map this all out in an incremental fashion in a lifelong manner. We'd like to be able to reason about occlusions and uncertainty, and we'd like these models to apply to diverse tasks. Finally, for those of us who are interested in building stuff on top of new representations, we need to build robust I/O. All right, so we need to be able to think about worlds that we build. One lab can build a world, or another lab can build another world, or I can build 5 worlds here. We can gather them all together and then learn from them. So if we have robust I/O, we can inspect what's happening with these new representations. I'm going to talk about some recent progress in my lab with my collaborators. We'll talk about 4 projects: adaptive graph, volumetric stiffness fields, structured gated metal learning, and also manipulation enhanced mapping that have touched on some of these aspects of these desiderata, but they're not fully touching the whole thing yet, but I think we're making good progress. So let me first start with adaptive graph. This is a deformable object representation. This is one of the most kind of interesting areas of manipulation nowadays. And there's lots of different ways that people are looking into modeling these types of deformations. And there's a big breakdown between analytical methods and data-driven methods. So analytical methods use constitutive equations and some kind of representation of the object meshes, like string mass systems, finite element methods, or material point methods. And with some nice things like Gaussian splatting or NURBS, you can get some really nice appearance-based deformations, well, replicate the appearance of deformations and also in a controllable manner, such as this bread tearing and this dropping of this potato. You can also look at just purely data-driven models of deformation, including graph neural networks, as well as image-based techniques and nerve-based techniques that represent the deformations as neural deformation fields. Now, these also have similar kinds of strengths and weaknesses between the kind of rigid world versus policy learning kind of approaches. The nice thing about analytical methods is that they're physically grounded. You can have fairly good spatial temporal prediction accuracy if you tune these well. And they also can generalize between object geometries essentially trivially. However, choosing constitutive equations that actually represent what objects do is a really, really big challenge. And also dealing with perception is a big challenge as well. And there's a complementary set of strengths and weaknesses for data-driven methods. So you can automatically discover physics, which is great. And you can also directly or nearly directly use perception inputs into your models. but they tend to have low precision, they tend to be somewhat unstable, they tend to not generalize very well out of distribution, and they also have smoothing and averaging tendencies. When you're training from a bunch of different objects, you just kind of learn like an average model. So the first project I'll talk about, Adaptograph, is addressing the latter two of these weaknesses here. So it's addressing the out of distribution generalization and also the smoothing and averaging tendencies. So this paper, Adaptograph, appeared last year. That's a joint work with Yunzhu Li and Kaifeng Zhang. What we did in this work is we built graph-based neural dynamics models. So these are graph neural networks that represent the objects as a set of particles with edges between them. And what we introduced was a material conditioning behavior where the positions, the future positions of these particles depends on a latent material parameter. And graph neural networks are quite diverse in the types of objects that they can handle. And so we applied these to rigid objects, ropes, granular objects, and cloths. We conditioned these on material parameters that are not observed, but they're trained with these material parameters known in simulation. And we trained this physical property conditioned graph neural network. Now, online, when we observe a new box, rope, granular object, or cloth, we can estimate that physical property and thereby get better predictions of how that novel object behaves. And so here are some examples of how this is working. So without this kind of adaptation step, this kind of box pushing with a kind of average model of a box doesn't do very well, but this object actually has a weight in it that changes its center of pressure. So ours does a much better job of aligning it to its target. For this rope straightening task, we also do a better job of estimating its stiffness and its frictional properties with the ground, and ends up getting better behavior. We can do the same thing for granular media as well as cloth relocating, ultimately getting higher accuracy for completing these kind of straightening tasks. This, by the way, the model is used in a planner. It's an MPPI planner, and this is used closed loop. After every manipulation, it's resensing the configuration of the object and continuing. Okay. So just in summary, this is a very flexible model. It's able to condition its model on the material parameters, and this is more fast and stable compared to fine-tuning. You only need a handful of interactions to be able to estimate reasonably good material parameters. However, there are a few limitations of this technique, which we are going to be addressing with the next project. So we're assuming that we have homogeneous materials, so that we're doing this optimization in a relatively low dimensional parameter spaces, which we can globally optimize. And it's also not really physically based, so it's not trivial to integrate tactile sensing. So for the next project, we started looking at these other issues, and actually we're going to be looking at an analytical model and addressing a couple of the weaknesses of analytical methods using this next project. So we wanted to address touch and heterogeneity, and we were inspired by a bunch of previous work, including this one by Charlie Kemp's group, Reaching in Clutter, and the Dimitri Berenson's group, in which they were using touch to figure out where obstacles were in space and using them to avoid obstacles with motion planning without using vision. So this technique that was introduced was actually Shah's work. The technique is called volumetric stiffness field, and we're here addressing heterogeneous objects like plants. So the model here is a volume of resistive particles, which have elastic behavior. We're using force or torque information, as well as the stick slip simulator, in order to form a forward observation model for tactile information. This model is approximate. Not all objects are just kind of floating particles in space that can be pushed and have springs. Objects are parts of the object are connected to one another, and it's approximate, but the estimation is very parallelizable. So this is runnable in real time, so about 10 to 15 hertz, with tens of thousands of particles just strewn throughout some kind of volume. And so you can see that as you touch the object here, you can see stiffness kind of appearing where the robot is feeling some resistive forces in its joint torque sensors. And so this, as you start touching more and more of the object, it gets to a better kind of approximation of where the stiffness lies within this volume. It can actually kind of push through soft stuff, estimate that stuff is soft, and then it hits a branch underneath and then estimates there's some stiffness there. Also appearing at ICRA, we have actually, I believe that's tomorrow. We have also a neural version of this called Neural VSF, which allows us to estimate with high resolution tactile sensors a more artifact-free version of this volumetric stiffness field. And so we're using this Punyo bubble sensor that has dense contact force readings, and then building a VSF representation of this object. This can be trained within a few tens of seconds. So it's much longer to gather the data than to actually train this model. So you can see that there's some stiff stuff that's modeling near the toe of the shoe, some soft stuff near the top of the boot. We can also use this for simulation. So if you wanted to simulate what would happen with a new sensor, then you can go ahead and do that. So that's what's great about these kinds of representations. We can also do blind localization. So if we have a object model that we've modeled in a kind of reference volumetric stiffness field, and then we cover it with some kind of cover, then we can touch underneath the cover and feel what's underneath the cover and localize where the object is. So if you ever have a backpack and you're trying to find something and you're reaching down to that and trying to feel for stuff, we're doing something very similar in this in this method. This is actually more accurate than doing things like having thresholds and of where things are hard and then trying to match those thresholds with ICP. One of the issues with tactile sensing is that tactile sensing is sparse, right? So you don't want to touch everything before you can recognize it. So we all want to link vision and touch. And so this next project is a Bayesian meta-learning approach to use offline data and build some sort of, like, I'm not going to say foundation model for touch, but it's getting closer to that. We're trying to learn a meta prior that we can use to then instantiate a volumetric stiffness field from just looking at an object and then improve that field by a few touches. So the way this works is that we have each element has some kind of feature vector. In this project, we used Dino V2 features, and each element also has an unknown stiffness, which is decomposed into a heterogeneous and some kind of latent part. The heterogeneous part, just like the vanilla VSF, is assumed to be an independent Gaussian distribution. And then this latent variable here there's a latent kind of material parameter phi. It's related to the distribution over the object using this matrix L, and we assume that phi has an independent Gaussian distribution that depends on the feature vectors. Now, what this really means is that we can encode a variety of different types of structural assumptions in this kind of representation. So we can, for just a purely heterogeneous object, we would have a diagonal covariance matrix for the stiffness. So this allows this EKF-based formulation of VSF to be quite efficient. If we want to assume that there's also a homogeneous component to this, where if I touch an object, it feels stiffer than average, I can essentially think about the whole object getting stiffer. And the way that we do that is by having this L matrix be just a single vertical column. If we do something like segmentation of this object into a bunch of, let's say, leaves or parts, then we can encode the segment identity, encoding as a sort of selection matrix in this L, and we can also do various combinations of this. Ultimately, the covariance is dense in the stiffness domain, but we're doing the estimation still with sparse matrices. So this makes this still fast. When we're doing meta learning, we're learning these distributions, the parameters of the distribution there, and this allows us to do a much better job of predicting the stiffness. And so what ended up happening with this method is that in zero shot, we're able to predict the volumetric stiffness field as accurately as about 10 to 15 touches using the prior work. So this is, and then this will also just get better. If you start touching the objects, the estimates will only get better. Just in summary, this is a real-time dense estimation for heterogeneous deformable objects, and we can also include meta-learning to do few-shot learning for this vision-touch correlation. We have some software support, this new library, OpenVSF, so please take a look at that if you're interested in getting to use some of these techniques. We've got I/O, common types of robots, common types of sensors, common feature spaces. Some of the limitations of this technique, though, are that it only supports elastic deformation. It only uses vision once at the start. And it only, so you also have to prescribe these latent spaces. So the last project I'll talk about is how we can work with mapping and using vision more incrementally over time. So now there's been a lot of great work in the object goal navigation literature in being able to predict where objects lie so that you can navigate to go and locate them. Now, also mechanical search problems where you have some kind of cluttered environment and you want to find a certain target object, you can use probabilistic inference of where what the robot has seen and what it hasn't seen to go and search for that object. And so the goal of this project is to investigate whether we can propagate map beliefs over entire scenes in 3D and through these complex manipulations. So this paper that will be appearing in RSS 2025, it will use voxel-based voxel-based map belief dynamics. This method that we're going to be somehow it's not playing. It's not playing. Oh, it was playing just a second ago.
Okay.
Oh, okay, it's now. Yeah. Okay, Zoom. Okay, here we go. So the object, so the robot here is scanning for kind of cleared out spaces, and it's looking for all the objects that exist in the space. But when it can't clear out those spaces anymore, it'll go and manipulate the objects to clear out some space. The internal representations that are being used are being shown here. So we have a bird's eye view mapping of semantics and occupancy. And we're then using this in a POMVP planner to help clear out the areas in which the robot has not been able to see. Just a couple of details on how this works. We have a viewpoint action prediction based off of a neural network that is trained off of simulation. And we also have a manipulation one that's also trained off of simulation and conditioned on the robot's swept volume as it executes a manipulation action. There's some details here I'm going to skip over. Overall, compared to other baseline approaches, this manipulation enhanced mapping technique does better in terms of, especially in terms of semantics. So here on the x-axis is the number of actions taken, including viewpoints and manipulation actions, and then IOU is shown on the y-axis. And compared to random actions, the map completion network gives you a big boost in terms of semantics and occupancy. If you are using information gain like we're using in our planner, you get a boost early on in this, but asymptotically the gains sort of peter out. But then with manipulation, you add an extra bit of gain with semantics, which makes a lot of sense because if I just kind of push things over to the back, you know, I still see that things are kind of occupied, and so occupancy doesn't really help. It's not really help so much. If I move things aside and I see what's behind another object, I am helping my semantic IOU by quite a bit. And also it transfers zero shot to hardware and also the YCB object set. So we're using the segment anything model for segmentation. And so our technique does a much better job of being able to identify the target object than the other baselines. So I hope I've convinced you that it makes sense to start treating the world as stuff rather than individual objects. And this has the promise to tackle some longstanding challenges. And really the key here is estimation. How do these chunks of matter interact with each other in the robot? How do we do this in one shot like this Chihuahua did? We're making progress in several dimensions, but unification of these different dimensions, it still remains a challenge, but I think it's a grand challenge for us for the next few years of work. What's next? Well, we're also trying to extend some of our models to fill out more kind of columns of that original matrix that I showed. We're trying to do large-scale deformable world modeling for construction sites or fields. We're also trying to extend the VSF model to granular, viscous, and plastic deformation. And also, we're hopefully getting closer to that vision of foundation models of stuff that we can transfer amongst each other and help robots understand the world that they're interacting with. And I'd like to thank my students and collaborators and funders, and some links here as well. Thank you.
Hi, thanks for the inspiring talk.
My question, I have two questions. The first question is about the adaptive graph. How to construct a graph? Like what's the input and output of the node? And like for the deformable object, you like a row, if you push the row, are the nodes same with the previous time steps node? Or they are not the same?
Yeah, it's both are very good questions. So the first question is about how is the graph constructed. So there's some segmentation that happens where the object is segmented from the background. Then the points belonging to the segmented foreground object are then downsampled using farthest point sampling to a certain resolution, and then edges are constructed between them.
Got it. Thanks. And another question is about what's the physical properties of the node? Like if a rope, you can measure the friction coefficient or something else.
Yeah, so there's stiffness and friction coefficient for the rope example.
Got it. And how to get these properties in the real world?
So we trained everything in simulation, and it's like somehow the simulation fit the real world. I mean, if you have a terrible simulation that doesn't look like the real world at all, this is not going to work so well. But if in the span of materials that were simulated, the real world was somewhere within at least the convex hull, right? They can actually extrapolate a bit beyond what the simulator can do. So if you don't constrain the range of that parameter, you can actually have stiffer or softer ropes in reality that then get fit by this model.
Got it. Thank you.
Thanks. I have a question about the work where you're touching the object and trying to improve your contact map. How do you decide where to touch?
That's a very good question. So I believe the current method that we used was just essentially sampling points on the surface of the object and just going about and touching all of them. But if you wanted to, the great thing about having these models is that they also include the uncertainty that you have in these stiffness parameters. So you can actually have also an information gain based criterion to select where to go next if you're trying to build a complete map of the object. Yeah.
Oh, thanks. Just following on that exact same work, how with the touching of the object, do you address the fact that after touching it, like the whole frame of it may have been shifted? Like, is that something is that a big issue when it comes to that kind of method?
Well, so in the work that you saw, the objects were fixed, so they weren't sliding around. That is actually what my student is working on right now.
It's like a tree, like it is. Like you know, sometimes if you push it too hard, it might remain bent permanently.
Oh, plastic deformation. So that's a different. So there's two things. So for household objects that slide as you push them, we're already working on that. For plastic deformation, it's more difficult because you have to also represent the internal sort of creeping of the material, and so it is more challenging. We're looking into it, but have not found a satisfactory solution that will lead to real-time estimation yet.
Keep it on the work.
How does this apply to objects like eggs, for example? Like where it's deformable until it's not, and then can you use this to learn?
So yeah, currently that's not something that we have looked into. So that kind of catastrophic fractures is not something we currently model with these approaches. It's a very challenging kind of thing to model because it's so binary, essentially, right? You get very little feedback before the breakage happens. It's actually kind of similar to friction. So we also, with these estimations, it's a hard estimation problem with any kind of gradient-based estimation problem to estimate these kinds of discrete changes of state. So both friction from going from stick to slip or from being intact to breaking, these are typically difficult problems. I don't have a great solution, but I'd love to talk to people who might have some ideas about how to address these things.
Follow up on that. Do you program the graph to change based on these physical properties that you've measured, and if so, how?
Yeah, so these are, so conditioning the manipulation actions on these models is something that we are looking into. I mean, it's fairly straightforward to do. It's just trying to look like what breadth of problems can we address with this. We're also looking into packing problems where you try to take a deformable object and some kind of packaging and squeeze it into some kind of container with a bunch of other objects. So that is another type of conditioning. How far do you squish things before you expect a breakage or damage to the object? Yes, so these models are great because you can condition on them. You can put them into objective functions for planners or constraints for planners. You could potentially put them into policies as well. If you can extract a representation that can be encoded into your policy, you may be able to condition based off of stiffness and other properties of the object.
Okay, Kris, thank you for the fantastic talk. I have a question. For some of the objects using graph neural networks, some other objects use this kind of deformation fields. Do you think like we can possibly have some unified way of representing all of them, or they need to stay separate?
That's a really good question. So actually, we're collaborating on things, and we have one paper on graph neural networks and another one based off of deformation fields. So I think it's going to be, if we're going to unify these, it's going to be some kind of different representation than either of them. I would love to kind of brainstorm about these, but like essentially the nice thing about graph neural networks is they encode this this inductive bias that they're translationally invariant, and also objects that are kind of interacting at the same distances will have similar kinds of behaviors, and also things that are far apart don't interact with one another. These neural deformation fields don't quite have those exact same biases. So, is it possible that we come up with something else? I think so. I think we need to think about correlations of how objects interact with one another. I am not quite sure how to deal with the potential quadratic kind of complexity. Actually, if you think about a world as being cubic, then all interactions between all points in the world to all other points in the world is n to the power 6th. So there's a computational limit there in terms of what we can really represent. But so I think there's something potentially like kernel methods or something. I have some ideas, but no like concrete outcomes yet. Thanks.
Yeah, for the sake of time, we'll move to the next talk.
Okay. Yeah, for the sake of time, we will move on to the next talk. And let's thanks again for Professor Kris Hauser's great talk. Okay. So let's welcome R.B. Negi for his talk titled "The Linear Contact Manifold for Accurate Port Estimation During Tagging or Insertion of Complex Geometries."
Okay, yeah, good.
Good afternoon, everyone. My name is Abhay Negi. I'm a PhD student at UIUC and a NASA NST Grow Fellow. And today I'll be introducing the concept of learning the contact manifold. This is a very general purpose representation which can be applied to many contact-rich tasks. And in this work, we'll be demonstrating it for assembly of complex geometries. So both model-based and learning-based methods work quite well for simple geometries with generous clearances. But when we come to very highly complex geometries with tight clearances that are below a millimeter, these methods tend to suffer, and specifically from jamming occurring very frequently. So to resolve this problem, we perform high accuracy pose estimation using only pose data and contact sensing. And the key idea here is our representation. So this concept is of the concept of the contact manifold. It's a simple idea that all poses of between two rigid bodies at which contact occurs forms a high-dimensional manifold in R6 pose space. Each point on this hypersurface is a pose at which contact occurs between the two rigid bodies. Now, solving for this analytically is highly intractable, so we take a data-driven approach here. We perturb the peg with respect to the hole and collect a large data set of contact poses. And we do this in the real world, but you can also use simulation for this. Now, online, when we're performing peg and hole insertion, we may begin with a pose estimate of the hole that's, say, 5 degrees or 5 mm in offset. That's good enough to get to partial insertion, but not full insertion. But we can get to partial insertion and perturb the peg to collect various contact pose observations. Now, we know that each one of these contact poses must correspond to a point on the contact manifold. But there's a slight caveat here, which is that because we have an error in our reference frame of the hole pose, the exact value of these contact observations don't directly lie in the contact manifold, but they are slightly offset from the manifold. But since we do know the contact manifold data prior, if we can find the matching points, we can align the pattern that we observe in the contact pose observations to our offline collected manifold, or map in this case. And one of the key insights is really seeing this as an ICP problem. So the same problem that we have in SLAM of aligning point clouds, we have here, except instead of 3D point clouds, we have 6D point clouds, in which each point represents a pose of contact. So we take the ICP algorithm, we feed in our observations of pose contacts and also our initial pose estimate. We align the reference frame using this initial hole pose estimate, and we find correspondences between our observation and a matching point on the contact manifold. And in this case, we first start with using simple nearest neighbor search. We compute some aggregate correction based on the error vectors to the correspondences and update our hole pose estimate. And we iteratively loop, improve our hole pose estimate, and this ends up working quite beautifully. We get very nice and accurate hole pose estimates, and then after that, we simply align and insert and get pretty good success rates. But the only downside to this is it turns out to be quite slow. The reason why is because nearest neighbor search becomes computationally quite expensive when the contact manifold dataset is on the order of 1 million points. And we need this many points to get high resolution in the contact manifold, which is how we get accurate pose estimates. So we implement a learning-based approach here where we train a neural network to perform a metric projection function. So essentially, we replace the nearest neighbor algorithm with this neural network model that takes in an input pose that is offset from the manifold and finds the closest point on the manifold. And this turns out to be 2 orders of magnitude faster, and also very interestingly ends up being more accurate, because essentially now we've fit a very smooth function to this contact manifold, and rather than getting the exact nearest neighbor value from our offline collected data set, we can now start interpolating in between our offline data. And lastly, a very nice benefit of this learning-based model is we can now differentiate through it using AutoGrad. So we can actually take an optimization-based approach rather than an iterative-based approach. And actually, that's some work that we've done and submitted to an RSS workshop. And lastly, when we put everything together and perform the peg and hole insertion task, we're able to get sub-millimeter and sub-degree accuracy in MAE. We also see a significant increase in success rate in comparison to performing insertion using only impedance control. And we also see that it's safer. We have much lower force due to better alignment. So ultimately, we demonstrate that using the contact manifold, we can perform accurate state estimation using only pose data. So that wraps up my talk. I'd love to thank my collaborators. This work was also sponsored by the NST Bureau Fellowship. And I'd also really like to thank my reviewer for this paper for giving their very constructive feedback. Thank you all for listening. I'll leave you with my key takeaways.
Look at how a very quick question if anyone wants to ask. Yeah, question. How is the contact measured on the robot? How do you get it?
Yeah, that's a great question. So we obviously get pose from joint encoder measurements, but to detect contact is very easy to do using either the joint torque sensors or a force torque sensor. And we just label it 0 or 1, whether it was contact or not. So it's quite robust.
Okay, thank you. We can go to the next oral presentation. The name of the presentation is Strategic Jenga Play via Graph-Based Neurodynamics Modeling. And the authors are Kavya, Puthuveetil, Yunzhu, Kazuto Yokoyama, Tasia Narita. And are the author available?
No, I haven't.
Me.
Okay, but I guess
I'm trying to get it.
have you connected to the HDMI cable?
Yes. Like I'm. Okay.
Good.
Okay, perfect. Sorry for the delay there. Hello, my name is Kavya Puthuveetil, and I'll be presenting our work, Strategic Jenga Play via Graph-Based Dynamics Modeling. Controls manipulation of groups of objects whose dynamics are closely linked, as required when playing the Jenga game, remains a challenging problem. In this work, we explore how we can leverage graph-based methods for manipulation in such scenarios, enabling careful extraction of blocks from a Jenga tower, as we can see here. We split the strategic Jenga task into 2 phases, both of which we tackle with graph-based methods. In the first phase, we attempt to understand the high-level dynamics of how removing blocks from the tower will impact its stability, allowing us to make decisions about which blocks to select for extraction. In the second phase, we learn a low-level dynamics model of the tower, which we use in a sampling-based MPC or MPPI controller to carefully remove blocks. We set up the Jenga task in simulation using the Isaac Lab framework, and we instantiate full-size 18-layer towers in the environment with randomized block dimensions and weights to match the distribution of a real-world set. We use a Franca robot arm to interact with the tower, first using a push stick to lightly nudge a selected block out of the tower. This initial interaction is executed by a hand-defined state machine. But once we've done that initial nudge, We grasp the block and use our MPPI controller to carefully perform that extraction. It looks like my video is. We'll see more of those extractions later on, but I'll dive into the details of our overall approach here, starting with the block selection model. We model block selection as a binary classification problem where we attempt to classify whether removal of a given block from the tower will cause it to fall. Our classifier takes in graphs where each node represents a block in the tower and encodes the 3 dimensions, weight, and a one-hot label of whether that block is an extraction target. Then we create edges in a directed fashion between a given block and the layer, the blocks in the layer directly below that block has contact with. We train and test our block selection model on a set of towers between rounds 1 and 15 of the game, which represents a challenging set of tower configurations, and we achieve a classification success rate of 75%. Notably, we achieve the success rate without using a graph representation of the tower that requires accurate localization of that 70 block pose. Now that we can reason about which blocks are safe to remove from the tower, we consider how to actually do that removal. For block extraction, we learn a dynamics model that takes in a graph that represents the tower. This graph is very similar to the one we use for block selection. However, this time we do use the 7D pose and we don't use the dimensions of the block. We additionally have a global feature that it represents the proposed action, which is a displacement of the end effector. Using this graph, we try to predict how the tower will be displaced. We use our trained block extraction dynamics model in our MPPI controller and achieved initial promising extraction accuracies for removing blocks from the tower. And then we also have higher control frequencies than if you use the simulator directly in this MPPI framework to produce samples. So here we show a sample extraction case on round 3 of the game. And this demonstrates some control that's reactive to those unwanted block displacements. Sorry, it seems my video is not working, but hopefully this next one works here. This one is where we're successfully performing extraction on a very difficult case where we have a precarious tower that's on round 9 of the game.
One minute left.
All right. So we envision a number of future improvements on the limitations of this work. One is to address this one failure case that we observed that stems from those initial interactions to lightly push blocks out of the tower. So since these pushes were executed in an open loop fashion, stuck blocks could cause misalignment and make it hard to extract the target block without disrupting the rest of the tower. So integration of the block extraction and selection modules, as well as doing the initial push with the closed loop controller could improve performance in these cases. And just to touch on some other future directions, I think there's opportunities to vastly improve the control frequencies by reducing the time taken to compose graphs, and then also leveraging contact information like is done in other Django work to aid in sim-to-role transfer. Thank you so much.
For the sake of time, we will move on to the next speaker, Yifan for his paper in adaptive compliance policy, learning approximate compliance for diffusion guided control. Let's welcome to his talk.
Thank you, everyone. My name is Yifan. I'm a postdoc working at Stanford University. Today is my great pleasure to present our recent work on adaptive compliance policy. So first, let me explain what is compliance. It is a useful model property that describes how motion responds to force. And very roughly speaking, having low compliance means the robot is stiff or rigid, and this is very good for doing precise tracking under force disturbances. On the other hand, having high compliance means the robot is soft or light. This is great for safely making and following compliance. So knowing those benefits, there has been a series of work on trying to compute the optimal compliance given a manipulation task. Although they work pretty well, they typically require knowledge of contact point locations, which will limit their generalizability. So in this work, we try to learn compliant behaviors directly from human demonstrations. Speaking of learning from human demonstrations, there has been a lot of recent success in imitation learning and foundation models. However, none of them explicitly reason about compliance. And in this work, we try to fill the gap by augmenting an existing position-only behavior cloning framework with forceful input and compliance outputs. Our policy would predict not only the reference position, but also a reference force and compliance parameters that can be executed directly by a standard compliance controller. The key challenge of this addition is how can we compute those compliance parameters from training data? At low speed, the compliance parameters we care about includes the stiffness matrix and the reference targets. Unfortunately, computing these two from force motion data is an underdetermined problem. There are infinite amount of solutions. In order to pick one solution that is useful, our key insight is that most of the time, one single arm only need to use almost one dimension of compliance in the direction of feedback force. This means we use low stiffness only in the force direction, while use very high stiffness in all the other directions. This particular choice of stiffness matrix has a few benefits. First, it gives us robustness against force disturbances in all directions, because now our robot is either having a high stiffness or experiencing a high contact force in any direction. Second, this method also guarantees the avoidance of huge internal force, so it's safe, and we have a theorem to prove it under null assumptions. And finally, this choice enables us to use a very compact and intuitive action space for the robot. It includes a reference pose, which is where the robot should be, a virtual target pose, which is where the robot wants to be, and a stiffness value. And all of this can be computed easily from force motion data. When the robot is in contact, the virtual target will deviate from the reference pose, and their difference will indicate the desired direction of force and compliance, and we can use it to reconstruct the full stiffness matrix. And when the robot is in free space, the two poses will coincide, meaning that our policy's behavior is the same as the original different policy. In order to collect the accurate force and motion data required to train the policy, we designed a kinesthetic teaching system with the force of sensor installed after a handle to record net force. The robot is put into zero stiffness and low damping mode, so we can easily demonstrate variable stiffness behavior. We test our method and compare with two baselines on the task of wiping ways. The first baseline is a compliant policy with uniform compliance. As we can see, the robot's motion gets affected by friction from the waves quick easily and has large tracking area. The second baseline we compare to is a stiff policy with no compliance. This time, the policy can easily trigger huge internal force and it quickly breaks the robot tool. On the contrary, our method is able to finish precise wiping regardless of friction while maintaining a safe amount of force. The second task we test on is flipping items. We test with a variety of items and different settings, and we run 100 trials per method. The compliance policy again goes all of distribution easily under force variance. And the stiff policy can sometimes work, but most of the time it can easily trigger huge force and goes out of distribution. The result is also a very low success rate. And on the contrary, since our method has both high and low stiffness, we are able to achieve almost 100% success rate, even for items that were not seen during training. So to conclude, in this work, we provide a method to label and encode spatial temporal varying compliance from demonstration data. It provides the following benefits to typical imitation learning framework. First is the ability to do disturbance rejection for force in any direction. Second is the ability to safely engage and maintain contacts. And also, we don't deteriorate the performance of the method when there is no force expected. So everything that works before should still work after you add force. And for more details, please visit our website or talk to me at the poster session outside. Thank you.
Thanks again for Yifan's great talk. And for the sake of time, let's start our poster session. And if you have any question about the papers I presented, during the contributed talk, please feel free to chat with the authors.
What was the raffle?
theory. And here I show you 60 samples. So you sample 60 and they're all concentrated around a few modes of those trajectories. So here we're predicting trajectories. I'm just showing the translation trajectories. And here we're predicting key poses. And you see we have 3 modes. All the 60 samples concentrate around those 3 modes because the student, one time he took the green grape first, the other the red, the other the black. So you have 3 main modes here in your data. And this very simple policy has very, very good performance in the standard simulation benchmarks like Calvin and narrow bench. And you know, we did ablations to understand where this benefit comes from. And it's very important that you reason in 3D versus 2D. And it's also very important to have relative attentions, okay? But both of them are very important. And whether you have 1 view or 3 views, it actually doesn't matter. I mean, it gives you a small boost, like 5%. I'm going to show in a little bit. But you can do all this 3D reasoning from a single head camera. And then we said, what about binomial manipulation? Can we extend this to binomial manipulation? And it's actually very trivial to extend it. You just now need to denoise 2 key poses for the 2 grippers or 2 trajectories. And other than that, the framework is very similar. At the same time, we did change from diffusion to flow matching, and we also did some accelerations on the architecture and so on to make our training time much smaller with respect to our previous work. And then we have this Paarth 2 recent benchmark that we want to score our performance. So the baseline we considered are as follows. So the first one that ended up doing the best is Pi0, where we took the weights and then fine-tuned the model to predict key poses because it worked much better when you denoise key poses as opposed to body joint trajectories, specifically for that RR bench, the RR benchmark and so on. And here is Paarth 2 and you know, DP3 like diffusion policy, 3D diffusion policy, very similar name to ours, but they don't have this position-aware attentions that is extremely important to give you essentially this good generalization. And also the whole thing is condensed into one vector, which is like a terrible idea. So the results are as follows. So here, the first set of results is on the left. So you see, despite the fact that, you know, 3D flow actor, so our previous work was 3D diffuser actor, we call this 3D flow actor, has not been pre-trained on an insane amount of data. It still, you know, scores really high on the benchmark, much higher than Pi0 and the other baselines. Yeah. You know, as I said, you can train on fewer cameras and it's still fine. You don't lose a lot of performance. And, you know, in comparison to using, you know, diffusion models, using flow matching is much faster inference. And we're able to cut training time by a huge amount. All right. And given these good results in simulation, the natural question is, what about the real world? All these foundation models, right? They are all 2D. All the competent ones are all 2D. What about 3D foundation models? So we tried to do that. And what we found is, you know, our method requires calibration, or at least the big benefits will come from calibrated robots. Calibrated robots means that the robot needs to know in the camera frame where its gripper is, or needs to be able to estimate it, because this is where the XYZ is going to be used in the attention during denoising. And the truth is that many cheap robots like Mobile Aloha, those that we could afford a year ago, you know, are not like very easy to calibrate. So even, you know, after a lot of calibration efforts, when the hand is extended, it has 1 centimeter off, let's say, okay? And so we use the wrist cameras not to aggregate 3D feature clouds because it was not super accurate, but we use it with 2D attentions. And we devised some, you know, tasks in the real world. This is us, you know, just collected 40 demonstrations on each one of those tasks. And then tested our model in the baseline, so on this real world data, again by fine tuning. And I'll show you how things look like. So what we learned, so all the other baselines were predicting body joint trajectories. Okay, we didn't have the time to adapt here the Pi0 to predict key poses to see if we can get to work better. But overall, it looks very reasonable using only 40 demonstrations. So I'll tell you what we're trying to do now. We're trying to get foundation 2D models like Pi0 and so on, and convert them into 3D policies. Okay, just change the attentions in the model. This is easy to do. The hard thing to do is to get 3D training data. Like we want to use this open embodiment and you know, bridge data and this RoboMind data set and all these data that are coming out. And each one of them is not well calibrated, right? And then they, they calibrate the data and become a tweet that, oh yes, look, I calibrated the data set for you. And the truth is that yes, calibration is actually very important. And this is also what we found. And here is how calibration is, you take the demonstration trajectories, they have annotated body joints, and this is great. But somehow what you want is to figure out where the gripper is in the camera coordinate frame. Even in 2D would be super useful, even in the 2D image space, as opposed to, 3D is even better, but even 2D would be useful. So here's how we solve this problem. So we do the auto-calibration pipeline. So this is Dr. Robot. This is a very nice paper from Paarth that essentially goes in simulation and trains up robot post-condition 3D Gaussians through rendering. Okay, so you take the robot model. First of all, you need to know what robot we're talking about. So you take that specific robot, render a bunch of images, and distill it into this neural network that we give it pose of the gripper. Okay, and it renders, it generates 3D Gaussians that you can render from every viewpoint to see how the, robot arm looks like. And once you do that, in a new video that you don't have a clue where the robot is, like its translation and rotation in the camera frame, you do analysis by synthesis. You do essentially, you minimize the reprojection error. So you optimize for the translation and orientation of the robot so that, if you render it under this rotation and translation, you're going to match the floor, going to match the RGB, you're going to match the deep features and so on. And indeed, this can solve your calibration problem, and this can work on the wild. So here is before the calibration, this is in Droid data, and you see that the ghost is not exactly on top of the gripper. And after the calibration, it is exactly on top. And you have like up to 1 centimeter error, let's say, okay? And, here in Droid, we do have some very noisy calibration initialization, but even without any calibration, like in the bridge data, you just do some grid search and this suffices. And we just try to accelerate now this auto-calibration pipeline. You give me an image frame and I tell you, body joints and rotation translation of the robot. So this is important for scaling up 3D policies. You want to get this data from, from real world data sets. Yeah. So I showed some results in the real world, and I just want to open a very quick parenthesis and say, now that we can auto-calibrate, essentially, we can translate any video into a simulation arena that we can use for having legit robot evaluations, large-scale automated in a simulation environment. So we've done this recently. And, we think this is very important, as opposed to each one of us comes and says, oh, look, I collected my 40 demonstrations on my 10 tasks, and here it is. Now we want to have, large-scale data sets that imitate training conditions that people can score, we can perturb, we can add perturbations on the environments, and see how different generalist policies perform and so on. Okay, so benchmarking is a big problem, and I'm just trying to say that recently we've done a lot of work in my lab of trying to solve that, because without benchmarks, then you don't have a clue which policy is good, right? So everybody can keep publishing papers as long as we don't have a way to compare with one another. There's no problem. But there is a problem in the field. The researcher doesn't have a problem, but the field has a problem. So the other big problem is how do we scale this real data, right? So I discussed about learning from demonstration, and we're not an industry that can afford having 100 robots around, with human users and paying the human users to actively collect demonstrations, seeing when the robot fails, intervene, and so on. This is pretty difficult to scale. So instead, what are we going to do? Well, what about simulation, right? And this workshop is about models, and explicit physics engines are also models of the world. And there's incredible progress in the graphics field on, and not only the graphics field, but the fine grained control and so on modeling this phenomenon. Right, and then the previous talks hinted on that. And what we've done recently is, take those algorithms and put them together into a physics engine that can, simulate a big variety of different materials. Because there are existing engines, Joko is ArcGIS, Sim is ArcLab, and so on, that are great, but they have some downsides. One is that, some specialize on rigid objects, some specialize on deformable objects, so you cannot have everything in one central place. And the biggest problem is that they are not very easy to use. You need to write many lines of code to just introduce a Frank arm in his ArcGIS, okay? So the Genesis initiative essentially is a way to, build a physics engine, explicit physics engine, not a learning-based one, that can handle a lot of materials, rigid, liquid, gas, deformable, thin shell objects, granular objects, and so on, with a lot of different solvers written from scratch on Kaichi, okay, GPU parallelizable programming language. And, with good performance, for articulated scenes, had very good performance. For piecewise rigid scenes, sorry. For deformable scenes, it's just twice faster only over, previous models. Good renderers that also are going to be GPU parallelized soon, and so on and so forth. So the question is, now that we have this physics engine, okay, this is the platform, this is not enough, right? Once you have the platform, who's going to generate environments for you? Who's going to put the materials in the right place? Who's going to generate the scene? And so on and so forth. You need to pay artists, and we're trying to get the human out of the picture. But now, to make simulation environments, you need insane effort from artists to do that. So in any case, so this is some preliminary sim to real result from Genesis, which we can skip. Okay, and yes, we very much believe on sim to real learning. But the question is, how can we automate that simulation building? Can machine learning help us on accelerating also that? And I think it's a really exciting time. I mean, me specifically, I've been working on 3D perception for some time. I mean, a couple of years ago, it was a huge revolution where first we were able, for the first time, we were able to lift any 2D, any 2D image into a 3D. So I'm going to show you now what I mean. So this is, up to 2-3 months ago, this is the results you could get, right? From a single image, you get immediately a 3D mesh of a shoe, right? Which is pretty difficult object. Now the problem is you don't have the laces being nice and soft against, a less soft shoe and so on. But guess what? This is going to be the next milestone. So now we can get from images immediately those 3D meshes, and we have recent work that also predicts structured meshes, like part-based meshes, and not just one monolithic from a picture, but a set of those meshes. Okay. And and here is what I meant earlier. So from any 2D image to 2 years ago, you can get a 3D differential representation using SDS, core distillation sampling, essentially using generative models to put constraints for viewpoints that you do not see. So this thing we've been saying forever, 2D to 3D is ambiguous and so on. There's no ambiguity once there is learning. Once you have your priors, everything is constrained. You just use these data-driven priors. And you can now make 3D meshes for everything. Like food, pieces of food, you cut the carrot, you take a picture, you make a 3D carrot and so on. Then you go to VLM and you say, okay, what physics properties I should put here, and VLM will tell you something, and you'll put it there, and the zucchini will be softer than, let's say, the carrot. And we moved on from there, and we say, okay, what if we ask visual language models also for task descriptions and reward functions? And once you have a task and reward, what you do is you just train PPM to solve the task. Okay, and this was one attempt. And based on this attempt of querying LLMs for tasks and Python functions of where the gripper should go and where the object should go, essentially you get a big you can generate data automatically without the human in the loop, essentially. Okay. Now asking VLMs for tasks is really not the right way to go. The most natural thing, and many speakers have hinted this, is you just watch a video, okay, of a human doing something, for example, pouring. And by the way, we cannot use VLMs to give us good reward functions for pouring, but we have videos that we can track. And that's another super exciting development, that video tracking started working, right? So we did this push with my student Adam Harley in 2022 with PIPs like independent particles, and said, forget about optical flow. You need to generate long trajectories from images. And, this like point trajectory prediction from video is actually super useful for robotics to instantiate rewards. And this is a recent work that you can get those trajectories now in 3D directly because we have such excellent camera estimation and depth estimation. You can use information from camera and depth and use this to iteratively essentially predict 3D point trajectories directly in 3D in a persistent 3D space, not in 2D image space, which is essentially all the time corrupted by camera motion. Okay. So now that we have the physics engine, the last thing we want to ask is the following. It's very similar to our previous speaker that said that there are two parts. One is this real to sim. You take the physical world and put it in the physics engine, and then you augment it and you generate tons of data. And once you generate tons of data and you know these worlds in the physics engine, as I showed you earlier, you can have in the same scene rigid and gas and fluid and so on, and very heterogeneous material interacting really well, of each one taken care by different solver. And once you do that, you can distill back the data to neural simulators to essentially generative model of 3D trajectories now, okay, that predict how particles move around. Yeah, so unfortunately we don't have we're not doing this, but you know we started working on that. So what we do is we go to Observers and essentially we ask ChatGPT for physics parameters, and then we give this to Genesis, and you know we simulate trajectories, object action interactions, okay, in that physics simulator, which then we distill. You know, as you generate a very big data set of that, so they look like this. So these two little guys as the fingers of the robot. You know, in general, you know, this should be way more general, but we start from a single gripper and one object, okay? And then you have essentially, again, a generative trajectory model. This is very similar to these graph-based particle models that you know, but it is generative. It is stochastic. You know, it can handle a multimodal distribution of output trajectories, which is terribly important to be able to share one model across a lot of data, okay? Because there are uncertainties, there's, you know, aleatoric uncertainty and so on. And the same uncertainty that this can model much better. So what this is essentially a diffusion model where you have your particle trajectories, which you encode, you add noise, and you know you try to predict back the noise essentially that you have added. That's it. And you know it's not a latent diffusion; it's like directly operated on point trajectories. And you know one way we handle this explosion of all-to-all attention on the particle space is you have this perceiver-like bottleneck. You have a set of latent variables where all the particles attend to those latent variables. Those latents are called the Z's. So X attend to the Z's, Z's attend between them, and then Z's go back and update X's. So instead of having X's updating each other. And we train two trajectory generative models, one that's conditioned on actions, and one that is not conditioned on actions. So in the second part, we try to model actions and objects jointly. And so you know, the action conditional model operates, you know, the same way that you expect. Like much like a simulator, you feed it actions. Unfortunately, my videos, okay, they run, but they're very slow. Okay, and the joint object and action model essentially can benefit because you can put object desired goals. I want this object to go to this specific location, and then those object goals through guided diffusion can go and affect your actions. So instead of doing this discrete search over action sequences, you can use guided diffusion, guided denoising to infer them through a single denoising process. And this here is one example. We have this original sample. We say, okay, I want to make sure that this, you know, whatever Q follows goes to the end location of this top left sample. And then we do guided diffusion, we infer actions, and we play them back in the simulator, and we see that we can generate the first sample essentially. So this is work in progress, but I just want to tell you that once you have an explicit physics engines, the whole point is to distill them back into large neural models over maybe 3D space, much like a physics simulator, but the neural one. So what did we talk about? We talked about how 3D visual reasoning can help action prediction by having these 3D bottlenecks in diffusion policies essentially, and view denoising to do position-aware attentions, okay, of those action tokens. And then we discussed of how we need to handle the calibration problem to be able to scale those 3D policies in real-world data, okay? And yeah, then we talked about real to sim, how we can take the physical world into a physics engine by using essentially computer vision to go from images to meshes and to trackers and to their trajectories essentially. And then we talk about going from sim back to real by distilling these physics engines back to 3D trajectory generative models, much like a 3D world model. Now, of course, this is like not even a step, you know, it's just that I'm telling you, you know, the desired future direction we want to go, that we hope that these 3D spaghettis, those 3D particles don't just change motion, but also change appearance. And you can learn from insane amount of both simulated data and real data. So with that, I want to thank the students that actually led this work and are, you know, funding. And, you know, of course, you that you invited me to present our work. So thank you very much.
For the sake of time, let's take one quick question.
Thank you so much for that talk. I think my question is more directed towards like this part of the process. Usually, like we've seen like large language models or VLMs are being really good at predicting physics and properties of objects. And most objects tend to be more constant, so they have multiple different parts of the object and have different subsets and masks that require different materials and properties. So like, what is the general like direction in terms of getting like the physics aspect of this process more correct to like VLMs, or is it like using like tracking from physics engines to sort of recalculate like a parameter unit kind of process?
Yeah. So first of all, about the geometry, let's discuss about geometry. So it's not like Gemini that's going to give us the meshes. There are other foundation models that map images to 3D meshes. Yeah, so that's number one. Number two, the way I think about the physics, I mean, of course, you can totally take an image and ask pixel-wise, give me physics parameters. And in fact, people have done that and it works totally well. You can just train models that for each pixel can generate physics parameters, and you can bootstrap this from your own physics data if you don't want, instead of just real data. Another way is that physics becomes implicit. As you make those models condition more and more on their history, right? And you are able to, to track and consume the history of what you've seen, implicitly you realize, oh yeah, this is like actually soft, or actually this is heavy. Much like quadruped working policies, they never infer explicitly the physics of the terrain, but implicitly, because they have access to long history observations, they figure out, the type of world they are in and adapt.
Yeah. Okay. Thank you. Okay. Yeah. Thank you again for Professor Katerina's great talk, and thanks again for the questions. Let's welcome Professor Ken Goldberg for his talk titled "Is Data All You Need? Large Robot Acting Model and Good Old-Fashioned Engineering."
Okay, thank you.
So,
let's see. Can you?
Oh,
can you hear me? Can you hear me all right?
We're able to hear you.
Okay, great. Now let's see. How do I share? There we go. How's that?
Yes, we're making you a co-host to make it easier. Okay, yes.
Let me just reduce this. Okay, one more second. I just want to try to see if I can reduce this thing on the left. How do I do it? Okay. Blood. I just saw this there. Hide the meeting controls. That's good. And then, can't get rid of the bar on the right, but you can see me okay?
Yes, we're able
All right.
to see you and your presentation.
All right. All right, great. Thank you. And I apologize, everyone, for not being there. I have a good excuse. My daughter just graduated from college today. So I'm up at her reception, and I'll be flying in tomorrow morning. So I'm really excited about this topic, and I'll stay for the panel discussion. This is something I've been thinking about a lot, which is this question: is data all you need? And first, I'll just acknowledge my students, many of whom are coming to ICRA this week. And the issue here is the huge amount of excitement and optimism around robotics right now, which is people are talking about $50 trillion impact on the world economy. And a lot of this is driven by this physical AI, the idea that there will be a ChatGPT moment for robotics. And a lot of people believe this is impending, this is imminent, and a lot of enthusiasm around it. They can be summarized in sort of this mantra that I've heard many times and may be familiar to you as well. People saying large data has solved vision, large data has solved language, and therefore large data will solve robotics. So I believe in a sense that this will happen, but my question is when. So that's what I want to talk about in this time we have. And I have I'm gonna do it in four parts. The GOFE stands for good old-fashioned engineering. So let's start with data is all you need. So this is really the position of a number of individuals who are very excited about the prospect of large models and end-to-end learning for robotics. That is, feed it in images and it generates control commands, and that if you train those networks on enough data, that will essentially solve all the problems in robotics. And there's some evidence that there's scaling laws that as you add more data, you get better performance. And this is what I think drives a lot of the optimism or the hope that data, if we keep getting more data, these systems will improve to the point where they basically solve the problem and achieve, extremely high performance of robots. Now, let's look at an example of self-driving cars. And the great example right now is Waymo. There's several companies in China also who are deploying driverless vehicles out on the street. And Waymo has a very good track record, very good safety record. And these are driverless cars. But Waymo called from level 4, by the way, not level 5. That is because these vehicles, there's no driver in the car, but there's remote access to drivers on demand, human drivers who are called in to help the car under certain circumstances. And it's not quite clear how often that happens, but some say it happens every several times an hour. But in any event, this is probably the biggest success story in the US. And I want to make a comparison between Waymo and Tesla. So Tesla is a competitor of Waymo and is taking a very different approach. They're collecting vast amounts of data from drivers and using them as essentially data collectors as they drive around, and they're sharing data back to Tesla. So there's estimates that Tesla has, because of that, about 9 billion miles of data versus 20 million miles from Waymo. So Waymo collects data by having test drivers drive around. So there's far less test drivers than there are consumers of Tesla vehicles. So it's about a factor of 500 to 1. So by the assumption that data is the most important thing, we would assume that Tesla would be doing far better than Waymo in terms of their robot performance. But in fact, it's not the case. So Waymo actually has doing much better than Tesla. And I'm sure there's a few people who will get into an argument about this or attack me on this, but I think it's pretty well, there's a strong consensus in the field that Tesla's self-driving technology is not nearly as good as Waymo's. And this is one metric, which is how far you can go before there's a disengagement. And I'm not sure about these numbers, but this is what I found online, but basically showing that Waymo is doing far better than Tesla. So the question is data all you need? Now, I want to say this because it really throws this into question, because Waymo has far less data and they're doing better. So what's going on? Well, I believe that it's not just a matter of data, but it's also this good old-fashioned engineering. And I've been told this by people at Waymo off the record, but that there are many modular systems inside their cars and many fail-safe approaches. There's a number of basically deterministic models that are running, model-based approaches that are running in parallel and providing checks on these systems. But there's also modules, filters on the various data collection systems, the sensors, like their LiDAR, et cetera, that are being used. So it's not an end-to-end system. It's very much of a modular system that combines data-driven learned approaches with good old-fashioned engineering. So that's what I want to make an argument for, that good old-fashioned engineering is valuable, this GOFE. And what is that? Well, it's modularity, number one. Basically, in engineering, we're taught to build modular systems. It has many advantages. They're decomposable. They're in some way encapsulated. So then we can concentrate, we can test each module, we can evaluate each module, we can track each module, and we can replace modules when a better one comes along. So that's kind of a fundamental cornerstone of good old-fashioned engineering, but it's also algorithms and algorithms that are deterministic that we can actually we can read through step by step and understand, or mathematically model and often make guarantees with. And then there's metrics, which are very nuanced and complex in good old-fashioned engineering. It's this is another whole side story I won't have time for today, but these are properties of good old-fashioned engineering, and I think it's important to think about and keep in mind because it works. And this is also, I just want to mention, this has been recognized in the field of systems, computing systems. This is a group from Databricks who published this paper a few months ago, basically saying that actually a lot of the AI systems that are out there are not really monolithic. They're not pure end-to-end. There's modularity in them, and so that they have subcomponents. If you study and look at them more closely, there's a lot of elements and nuances in their actual under the hood. So they're saying that's something we need, and actually we need to develop a better approach to. So it's very analogous to what I'm advocating for here in our field of robotics and automation. So what I'm saying is that how can we think about these together, namely model-free methods, data-driven methods with model-based methods, which are more based on analytic models. And another data point is the OXE, the OpenX embodiment effort that was featured at ICRA last year, and combined lots of research from many groups, lots of data, vast amounts of data together to build models. One thing that was interesting, if you zoom in on what kind of performance was happening, these models, they claimed paper, which I'm a co-author, so I'm going to take part of the blame for this, but one of the things that was stated was that there's 160,000 tasks, and if you do a histogram looking at the different tasks and you sort them essentially by keyword, because these are all used with language as well, they have descriptive phrases and words, they almost all were described with picking, moving, pushing, or placing. And so in a sense, I mean, this is a huge long tail distribution where almost everything is centralized around pick object 0 and place it in object 1. And when you think about that, that's an interesting task for sure, maybe with different objects, yes, but it's also very much very well understood in robotics. And this is chapter 3 of Russ Tedrake's textbook, but you can find this in other textbooks as well. There's a whole chapter, basic pick and place, which is basically pick object 0 and place it in object 1. And the classic good old-fashioned engineering approaches to that are very modular, is using computer vision, using robot grasping methods, then motion planning to achieve pick that task. That is very, very well studied, and they're very good solutions for it. Now, so I want to just contrast this good old-fashioned engineering with this new approach, which is being claimed to supersede it. I've even heard people say, well, actually one of my students we were cleaning the lab out, and she said, let's just get rid of this. I was like, no, there's still some value here. And this is, but there is a real viewpoint out there that the handbook is obsolete. And so I want to push back on that. I'm sort of summarize it this way. This is these cool new large models that are out there, very exciting with a lot of promise, very fancy, but this is good old-fashioned engineering. Okay, it's just basically, it works, and it's solid. It's been around for a while. It's pretty simple, but we can prove things. We can show that it works in a variety of conditions, and let's not disparage it or throw it out without being thoughtful. So what I'm actually advocating for is combinations of the two. That there's a lot of opportunity to think about hybrid methods that involve both. They have data, and so there's learn modules, but there's also good old-fashioned engineering modules. And how can these be combined together? So the goal is the general purpose robot, right? I get that. I see why it's appealing, and I'm not saying that this will not happen, or that we won't ever achieve it with data. The prospect of the sort of end-to-end model is very appealing for many reasons, and I don't want to be accused of sticking my head in the sand. I know that some of the younger generation and some colleagues might say, "Wait a second, you're fighting us. You're against this new trend, and you're just in denial." Well, I'm not. I accept it. In fact, I fully accept what's known as the bitter lesson from Rich Sutton, who won the Turing Award this year, which basically says the data-driven methods have won out again and again in many different fields and areas. And computer language, natural language processing, computer vision, speech recognition, it's true. And so it will, I think it will, I won't deny that it will eventually happen in robotics. But this is my big question is, the data will solve robotics, but the question is when? So I wanted to do a little bit more digging into that question. And so my students and I developed this little demonstration of this, and I'm going to play this for you right now. It's a comparison of the amount of robot data that's available today with the amount of data that goes into the large language models, VLMs. So here, I'll just play this. This is a Google model. Attention, the OXE. This is physical intelligence around November. It's in hours of data. Convert the amount of extra images in GPT-1 to hours of data, and then 2. And so these disks are roughly to scale. You see that the robot data is shrinking on the left corner, lower left corner, and making room for the size of these large models. So this is like one of those planet star comparisons videos I love from YouTube. But you're getting the picture here that these data sets are quite vast compared to what we have available in robotics. And so you can see on the far side of that, if it's not blocked out, that the range here is enormous. So I can share this with you later, but the bottom line is that there's about 100,000 year gap in the amount of data that we have for robotics so far. And it's really important just to put that into context, right? We have vast amounts of text and images on the internet, and the amount of time it would take a human to read all that stuff would be about 100,000 years. But the amount of data we have for robotics, we just don't have on the internet. So we have to generate it. And so the question is, how are we going to get this data to this vast amount of data? Now, there's 4 ways. One is simulation. Okay, one is that we can simulate and we can run through lots of scenarios, and that works really well for UAVs, flying vehicles. And so then you can simulate, and then you can execute the resulting policies that may have been learned with RL or other methods, and they work beautifully. It also seems to work really well for locomotion, and so we can train them in simulation and then execute them in real. And the sim to real gap seems very nicely surmountable. This is just empirically true. So these kind of results that we're seeing now from all the dogs and the humanoids are, their ability to locomote and do, acrobatics is astounding. There's no doubt about it. And that's really largely due to the ability to simulate and collect lots of data that way. But for manipulation, it's very hard to simulate. And we can go into more detail about this, but I think it's very well agreed upon by everyone in the field that you can make things that look good, but to actually make them actually perform physically accurately is extremely difficult. And it has to do with the microscopic effects that are very difficult to get right. And when you have collisions, which are inevitable if you're going to do manipulation, getting those collision dynamics right is very hard. Friction, extremely difficult to model accurately. And so when you do things, the sim to real gap is very large with manipulation. So it doesn't seem like we can just simulate. The next one is YouTube video. So there's a hope that we can just observe videos and extract 3D data from that. And this is sort of the hope. NVIDIA Cosmos is an example where they scanned in 20 million hours of videos. The problem is, I mean, that's very good for predicting the next video frame, which it does fairly well, but it's not at all designed to extract three-dimensional structure and collision dynamics or robot commands. So there's a lot of people working on this in computer vision, but it is by no means solved to be able to take video and now extract what is happening in the six-dimensional space of interactions so that that could be useful for training robots. That is by no means solved so far. And it's not clear how to solve it. It's not just a matter of more speed. It's really that we have to get better physics models, and we don't know how to do that yet. So even the state-of-the-art Isaac lab does not offer really any modeling of contact dynamics at a low level detail or of deformations. Now, the other way of getting it is what I alluded to earlier, human teleoperation. This is what physical intelligence and other companies are doing, teleoperating with humans. And that gives you very nice quality data. So you can basically have cameras monitoring what's happening and then giving it robot commands, and you're basically then using that to train a system to generate robot commands in the future. With given video, images, and text, they'll generate the appropriate robot motions. So this is good, decent performance. This is what I mentioned earlier with the OXE model, and physical intelligence showed some pretty interesting results last fall. But again, this is a result of approximately 1 year of data. So they have many people working on this, different robots, different shifts, but in the amount of 6 months, were able to generate about 10,000 hours, which is about a year's worth of data. So it's nowhere near enough. And Google has also been generating data, collecting data internally. And so they announced Gemini, and they didn't specify how much data they have. But again, it can't be much more in terms of just years. If we're talking about teleoperation, it's in that same category. So there's a huge data gap. So how are we going to do this? And I want to just mention one last approach, which is a stepping stone to getting this amount of data. And here's the idea: is that instead of these first three, we consider real production. And that is, we put out real robots in real scenarios. And then we let them run and we collect data from those. So one data point here, I think this is what Waymo is doing now with their cars, collecting real data as the robots run. But also, company that I co-founded, Ambi Robotics, has a system that has been out for 4 years now called Ambi Sort. And what it does is it sorts packages in e-commerce settings, and it's being used by real customers who are paying for the systems. And this will be featured on Thursday. It's getting an award from IEEE RAS for product innovation. But this system has been sending back data since its inception. So far we've sorted about 100 million packages over the last 4 years. This is with 80 some machines working around the clock in real production facilities. And that data is all being sent back to our central servers. And so this amount of data is roughly 20 times more than physical intelligence reported in the fall. And so it's about 200,000 hours, which is about 22 years of data. So that's, in a sense, this very valuable set of data that's actually not teleoperated. It's real robots operating on real data, real environments, real packages. So that data set also can be used to generate a large model, to train a large model. So we've done that. We've only used 1% of the data because it's very expensive to train these models. We don't have the budget to do it as yet, but we trained a small model with 1% of that data, and it outperforms our previous methods that were trained with sim to real methods. So it's very promising, and we're actually seeing some scaling effect here that as we add more data, the performance starts that is improving. So we're excited to continue this and see where that tapers off. But the idea is that there's a data flywheel. So what we do is, we build a system that's good enough for customers and has a attractive return on investment. Then customers essentially buy that, put it into practice, and that generates data that then can be used to develop next generation of systems. And so that's what we've done most recently. Our new system is Ambi Stack, which is a SQL. It's sort of a dual to picking, but here the challenge is how do we stack objects, packages effectively and efficiently. So here's the real system in operation. Just video, but it's basically has to solve a Tetris problem. And Tetris is known to be NP hard in 2 dimensions, but it's even harder in 3 dimensions. So this is what we're trying to do, is reduce the amount of empty space. So here's what that looks like if you have 35% empty space, and here's a packing that's 90%. Or sorry, 90% full versus 35% full. So what we're trying to do is maximize the space usage, and that's very valuable. It cuts down on the amount of space and time for shipping organizations. So this system is also benefiting from this data that was collected and has an interesting perspective for the future. So I'm going to end there, and I don't have time really to go into this analytic architecture, although I'll say very quickly, coming back to combining good old-fashioned engineering with learned models, there is an architecture that my students and I developed that was published in IROS this year, or last year. It's basically a modular approach to adding modules that can be either learned or good old-fashioned engineering, and talks about how to insert those modules. So we have a case study with bagging, and we were able to show, again, I'm just going to speed through this, but we're basically be able to show that when we add a module for a very specific failure mode, that we're able to increase performance dramatically in this particular task. So it's a way of doing this. We've also applied similar thing to cable untangling, and similarly, we've been able to show that it's very helpful. So happy to talk more about this this particular approach, manip, but it's in IROS, and I think it has a reasonable model for being able to think about these 2 things not as oppositions or 2 different dogmas that are incompatible, but actually something that could actually work together. Okay. So I'll just leave you with the robot data gap, and happy to take any questions. Thank you.
For the sake of time, let's take 2 questions.
Okay, I'm not hearing anything, guys.
Are there any questions from audience? Okay, yeah, there is one trying to grab the microphone.
Hello. Thank you very much for the very, very nice talk. I was wondering actually, for the case when you trained on the data you collected from your robots which are deployed, why do you think the model managed to perform better than the others you have? Because you have mistakes in there which you can learn from, or what's kind of the main aspects which have?
Oh, great. Okay, great question. Yeah, absolutely. You do need mistakes. You actually need, mistakes are very important, in fact. If you just have positive examples, it's actually very difficult to train a reliable model. So you need negative examples as well. The difference is that in a prior system with Ambi was based on a sim to real model with injected noise, and so to give it robustness. And that worked surprisingly well, got us up to in the realm of 90 plus success rate for picking up bags and boxes. But to push that higher and to increase the success rate is very, very challenging. And I want to also re-emphasize this, and for anyone you know, when you look at these success rates, it's very nonlinear, right? It gets very hard to push. Once you get up to 90, going from to 91% is, you know, extremely hard. Going to 92 is much harder. So it becomes very, very challenging to push those success rates up. And in this case, we found though that because of the system is looking at lots and lots of examples, it's able to look at, in particular, bags, which are very difficult. We were not able to model those in our first generation of it was an extension of DexNet. And so bags have wrinkles that are very nuanced. So we would often pick points for suction cups near wrinkles in bags, and they would fail. So this system, the system has seen 100 million examples of picking. Often many of those are bags, and it learned how to avoid those wrinkles. So that's one example of what's going on. Again, we can't look into the system and understand what are all the nuances, but it's just real data from real environments, real packages that was much higher quality than what we were able to simulate. And the performance empirically is that it's something on the order of, it brought us up several percentage points in success rate, pick success rate. Does that answer your question?
Yeah, I think the audience said yes.
Okay, great. Yeah, no, it's a great question, and thanks for asking it.
I would have one question about the telemetry, the data you guys collect from the field robots. What specifically would be the type of data that you collect, and how do you think about data storage versus the utility of the data? What type of formats are you looking at? And
okay, great.
That you can share about this in a practical sense, because it is
yeah,
we say it, but we don't actually, devils in details.
Yeah, no, you're absolutely right. I will tell you, first of all, and I didn't mention this, but I will share with you, we didn't start collecting this data because we thought it would be useful for building large models. This was 4 years ago. What we did was we initially started collecting it for maintenance purposes. We just wanted to watch all these machines so that if anything went wrong, we could see it and we could try and correct it, because uptime is a big metric with the customers. So we would see, for example, that a suction cup would start not performing. We'd see drops, and then we would know that the suction cup got clogged, or something changed with the lighting or something like that. So we were just using it for essentially, anticipating maintenance. And so, but we stored all of that because we get all this data. We get 5 camera images of every time we look at a bin. And so all those images, because we're using it both we're scanning for a barcode, which is another source that we were just doing it for practical reasons, but we just ended up saving all that information. And it was fortunate because that data, it's a petabyte, right? It's not enormous, but it's a fair amount, and it requires, streaming services, and we don't collect it all in real time, so there's a little bit of buffering. But all that data we were storing it away in the cloud. And so that provides, again, this very large resource. Now, exactly how we stored it is a good question. And it's not that I'm trying to hide this, but I just don't know. I will mention that this is a topic that my student we've been looking at for the context of the OXE data. And there's a paper that'll be out tomorrow called RoboDM, Robot Data Management, that is going to be on the Tuesday morning track. Robo-DM. That is all about data standards for robot data. And I think that your question is very insightful, because it's very important, and I think it's been understudied. There's many naive ways to do that, and then there's opportunities for improving that data storage and data management efficiency in many different ways. Just also to be able to store it, but also search it, index it, and make use of it for training. So that's a great question, and I hope that's a part of an answer to you.
Thank you. Yeah, the audience.
Thank
you. And
great.
Thank you,
Okay.
Professor. And over great talk.
My pleasure. And I'll stick around for the panel too, if that's okay.
Okay, so now, we'll start the panel discussion, roles of physics-based model and data-driven learning in context-rich manipulation. We will have Professor Yunzhu Li as a panel moderator. We will have Paarth, Ken, Kris, and Katerina as our panelists.
Okay. Hey, Katerina. Hey, Kris.
Okay. Is the camera all right? Yes.
And after the panel discussion, we will have Professor Yunzhu Li to announce the award and the best paper award finalists, as well as the best paper for the contributed talk, chosen from 39 submissions. Yes, let's do that.
Oh, it's not sharing the it's sharing like this presenter view instead of the across screen.
Yes. Okay, it's working. Oh yeah, now it looks good. Yeah, so we can get started.
Okay, so thanks everyone for staying until now. So now we are entering some of the most exciting parts of today's workshop, which is panel discussions. So just to reintroduce like all the panelists, we have Kris Hauser. He's a faculty at UIUC. He has already been talking to us about the modeling of stuff, deformable objects, robes, like stuffed animals, like shoes, etc. We also have Paarth, like he is with Toyota Research Institute. He has been talking to us on their development of large behavior models and how they are using the Drake, some physics-based models in order to do co-training and validations of the learned policy. We have Katerina, she's with CMU. She has also done, she has also introduced to us on her work on doing like 3D semantic representation of the environments and sim to real distillations of different types of models. And we just heard from like a Ken from UC Berkeley on the data versus like a good old-fashioned like engineering. So super excited to be the moderators. Like Ken, you have been like on panels where been moderating panels. I was like the panelist, so I'm super honored to also be able to moderating this moderating this panel. So I will start with my first question, which also like alluded a little bit in Ken's talk. So we know from many other domains, for example, especially in locomotions, the model doesn't have to be perfect. We have simulations that doesn't simulate snows, that doesn't simulate bushes, but with enough randomizations in simulations, you get policies that can work very, very robustly in the real world environment in some very challenging scenarios in the locomotion domain. But such lessons haven't really been transferred or at least observed as powerful in manipulations. So my first question is, how accurate does a model has to be for you to like transfer really like robustly in the real world environment?
Do you want to go first or want me to say something?
Go ahead, Katerina. I was hoping you're going to say something because I know we're going to lock horns on this one.
So there is a difference between locomotion and manipulation. In locomotion, you walk and you apply force to the ground, but you don't care to model how the ground deforms as a result of your forces. For manipulation, we very much need to model how the world changes as a result of our
interactions. All right, so this is a huge difference. Yeah, so that's number one. This makes things harder. Number two, why we haven't seen big systems yet? Well, to be honest, I mean, they have started coming out. There's another workshop in the morning, for example, on yeah, contact reach, like Dexterous multi-finger hands. And in fact, there they were saying, you know, teleoperation is actually impossible. You know, we really, you know, have much bigger progress from simulation, and they did show some great results there. Now here is one suspicion, which I'm not sure. Actually, I'm not sure. People are working on large-scale sim-to-real for parallel job. It seems to me the multi-finger has a benefit, much like a quadruped robot has multiple legs, and this allows you to sense the environment, like we have this proprioception. And this history of proprioception is actually very important for adaptability of the policy, right? It's all about the history that makes the sim-to-real adaptability work. Okay, so it might be that this multi-finger hands may be, you know, more important, maybe important for such sim-to-real, exactly due to this proprioception history that they can give, where the fingers land essentially allow you to understand better the material. I mean, that's one reason why. The second reason could be that, you know, more force sensing or tactile sensing might also be important for manipulation, and that's why, you know, we haven't seen some results. But I want to say that in the next 6 months, I think we're going to see incredible manipulation systems coming from sim-to-real. I mean, they're already started, let's say. Yeah, so I think it's also a matter of time.
I think one other consideration that needs to be taken into account is the precision of the task. For example, in locomotion on flat ground, you can kind of stumble and recover quite easily. Whereas if you're a mountain goat on the side of a cliff, making one misstep will be fatal. And you know, I do rock climbing myself, and if you're to try to train rock climbing in simulation, I think you'd have a hard time transferring from sim to real. Similarly, for many of these manipulation tasks like peg and hole, the precision of the task is really the key. You know, motor babbling or making mistakes with a neural network will cause you to have a very small fraction of good data for you to be able to get reward on. So I think that's kind of the main consideration there.
Okay, I can jump in. I mean, I think, you know, I hope Katerina's right. And Katerina, I know we had a really good conversation a couple of weeks ago at Carnegie Mellon, and I like the way you're thinking about simulation. And I think there is a lot of hope that we will be able to overcome these challenges. I'm really not sure about the aspect of multi-finger, because to my mind, at least my instinct is that makes the problem much harder, that you have all the more collisions and uncertainty arising from those additional contacts. That you also said something about having more, you know, sensing perception, and that's interesting because, you know, the thing, you have some idea of perception on a foot, right? That generally gives you maybe a surface normal of a contact, right? But generally, you're not getting a lot of nuances about the type of contact on the ground, if it's an edge contact or a point contact, et cetera. And that seems to be very important for manipulation. Just as Kris said, I think it matters the detail, because a very small change can have dramatic effect on whether you're holding something securely or dropping it. So, whereas I think that's much less the case for locomotion. And so, again, I don't fully claim to know the reasons why manipulation is so difficult to simulate, but empirically it seems to be the case. And when I'm I mean, again, I'm not trying to be negative about simulation. I'm very hopeful, and I think, you know, Haunan, as you said, that if you inject noise into those, you know, domain randomization and other methods could be added to make this work. I hope that works, but I'm not optimistic. In other words, I think we might be here next year, and Katerina, we'll have to make a little bet on this, side bet on this, but I think we'll be here next year and we'll be saying the same thing, that we're still, that it's not quite, you know, it hasn't had the kind of breakthrough that we see with locomotion.
Yeah, so I think it's mostly just a matter of time, to be honest, as well. I think a lot of what you see in like one of like the issues that you're seeing in like manipulation with like using it in sim is also like reward modeling, sparse rewards. That's like a general issue like you're seeing when we kind of like are mostly doing things with blocks and whatnot. I just think it's a matter of time before we use some sort of like more like larger common sense model. Like there's like generative value learning and stuff that was out there, was like put out. There's a lot of work that's going on behind the scenes that's kind of like using some of these like types of like more common sense reward modeling that I think will just like get us a lot further. But I think also like the sim to real gap and like locomotion, it's like it's a relatively new thing that 5 years ago, that's still relatively new in like the context of things. And I think as we like understand this more and use this and apply this more to manipulation in more nuanced ways, someone's going to unlock it, and it's just a matter of time.
Actually, one last thought. So no offense to anyone NVIDIA, but you spend more time trying to get Isaac Sim to not blow up than to actually get good data when you try to set up a new scene. So once we get that down, you know, I think maybe we can make some progress. I'm not this is not exclusive to NVIDIA. It's also Drake and Clamped and Gazebo and whatever. Yeah.
Yeah, from my observation, like from a few years ago, like from OpenAI, they have already shown like sim-to-real transfer can work on multi-finger hands for dexterous manipulations. And since then, direct sim-to-real transfer, like again, like I'm still a little bit cautious, optimistic. I see a lot of like valid points here in like how much value, and maybe it's just a matter of time. But I still feel there might be still some kind of fundamental issues out there. For example, if in the simulation, if you push something, the object rotates for 10 degrees, but in reality it rotates for 12 degrees. It may not matter that much. But like Kris suggested, if in the simulation it blows up, or if the object slipped away between your fingers, but in the reality, the grasping was successful, that probably is an issue. So like where and how to close the gap and what type of gap matters might be an important considerations. So
can I just ask what you said sim to real worked for OpenAI? I'm just wondering what are you referring to? I'm
referring to like learning dexterity and rotating Rubik's Cube.
Oh, but the Rubik's Cube story was very, I don't think that was considered a success story of sim to real. Okay, we could talk offline, but I would really question that.
Yeah, I totally see your point. I also looked at the paper. If you look at the paper, they probably tried 10 times and succeeded maybe for 2 times. If you report they tried 10 times, possibly they tried much more than that. But since then, we have seen many other works, like works including like visual dexterities, etc., that start to show some sim-to-real transfer of dexterous manipulation. So then I guess my next question is about the specific instantiation of the model. So today we have been hearing about like the physics-based modeling and also learning-based modeling. So I'm curious about from the panel, like what do you see the role of learning play, and what type of role does physics plays for us to getting the type of models that we want that can deliver us the right levels of robustness for this type of like a model to reality transfer?
I guess you could say that physics is just learning passed through dead European white men. You know, that knowledge is passed on and distilled and so on, and then experimentally verified. So you could certainly say that, you know, learning can learn physics, right? And hypothetically it can. But just like Ken said about good old-fashioned engineering, we might as well make use of laws that we know to be true. And this will only help us in the short term. Maybe eventually, as our data kind of grows to the point where we don't need them anymore, then that's something we can dismiss at some point.
Yeah, this is a great question. Number one, we humans don't have very good accurate physics, or we have intuitive versions of physics. The example that Professor Atkinson likes to give is that each one of us can understand what they can swallow and what they cannot swallow, but nobody has a physics and geometry aware model of their throats. So it's really intuitive, okay? So basically, we do need models that generalize. If we had models that generalize, so mu0 that condense the image in one vector, this latent, the dynamics models, they just didn't generalize on the driving environments or in general environments. If we'd find some dynamics models that would generalize, that's all we need. I think we'll look at physics simulations to get inspiration of inductive bias. So, modeling the world at the particle level seems to be interesting. The locality inductive bias, the prediction entity might be or might not be relevant for who knows, okay? So getting inspiration from the physics and modeling is interesting, as well as getting data, exactly what we said, that the short term, we need this data coming from physics engines. And of course, the most interesting direction would be how can we merge the two? So we don't need to really model the bolt and the screw really accurately to get this to work, but rather by combining real world data and simulation, we can really quickly learn this model that has some part of more explicit physics and some part of implicit and more learning-based components. But unfortunately, I'm not sure right now how to do that.
Yeah, I mean, just like playing around with Cosmos, it's like very obvious to me that like a lot of these big models have a lot of like physics intuition. Like I can see and like just give it text and it like does very like common sense things most of the time. And I'm like pretty bullish that scaling that up and continuing to scale that up is like the right approach. You put in actions and it probably will understand some level of like dynamics. And I think that's just naturally going to pop out. I would say though, there's like, okay, so when I presented some of the videos of like the cutting the apple task at TRI, behind the scenes is like, there's an inverse kinematics controller with like model that has a purely model-based control. And I would say that's one of the biggest reasons we're able to actually do a lot of these tasks is that we have a very good model-based controller underneath. So kind of going back to what Ken's been saying, good old-fashioned engineering, and that lets us actually scale up and like collect some of these tasks and do it like in a very like meaningful way. And I think that's where like you're going to see a lot of these like models come into place. It's like you really need to fundamentally understand these. You really need to understand how they work behind the scenes, have a good intuition for tuning these things. And I think that takes you a long way until like data starts to like take over. But I really for now think that like having these like tools in place is like really important and will be necessary for like quite a while.
I really appreciate you saying that. That's actually great because I just saw Russ present the apple cutting. And it is super impressive. Also the part with the putting the gear on the bike, the bike repair task. And I'm very impressed. And it is interesting to hear that you can achieve those with good old-fashioned engineering, right? Obviously, Russ knows how to do that as well as anyone. And then you're saying, if I heard you right, that you can then you use that to bootstrap, right? Because you get executions that you can then learn from. And that's exactly, I think, the right approach, right? It's being able to get something running, then use it as a flywheel to generate lots of examples, right? So I think that's really, really exciting. I just want to comment on what you said about Cosmo, because so Cosmo, let's just look. I mean, you can generate very realistic looking dexterous manipulation and with hands. There's no doubt about it. We know this because this is I think part of why it's challenging, because it's very easy to be deceived by the visuals, and Hollywood is very good at generating computer graphics that look amazingly good to us, right? And we're like, that looks perfectly fine, but I think it's really important to be have our guard up about this. So here, I want to throw out, in the spirit of Katerina's example of the swallowing, an object, but here's a just specific thing to keep in mind when you look at videos and think about real to sim. But let's imagine the following task. Let's say someone hands you a handful of keys, a keychain. And the idea is just take those keys and line up all the keys so that they all have the teeth facing the same way. Okay. And generally, most people that assume they're not initially in that configuration. So now, what that means is you have to turn around and you have to take each key off and sort of turn it around and then put it back onto the key ring. I think that's going to be a very long time before we have a robot that could do that task. And I mean, that is very close to the alpha puzzle kind of difficulty of manipulation. And I don't think we're going to get there with simulation. I don't think we're going to get there with teleoperation. I don't think any dexterous robot, the hand, is going to be able to do that task. I think I just want to throw that out as a sort of just a reality check on how nuanced human dexterity is and how far we are from achieving that. And so we see a lot of amazing things, but we have to keep in mind, is that really going to get robots to be able to reproduce it?
Yeah, those are fantastic points. So of course, like there will always be tasks, for example, like the keychain examples, like it is very, very hard to get it done or get it completely solved. But maybe you can start to do something. For example, Ken, you have MB Robotics. It's starting to do some kind of like bin picking, bin sorting. I'm pretty sure also at Toyota Research, you guys probably is also inspired by some of the applications maybe Toyota has been facing. So I'm just curious, like for this type of model-based approach or the use of models. So is the model currently like sufficient for us to start tackle some like a very complicated like real world challenges or real world applications at an extent that can satisfy real world business needs? For example, I'm specifically curious, like for example, Ken, like in MB Robotics, are you doing physics-based simulation of those contexts? Or it's mostly about the simulations of, for example, the efficiency, the throughput of the entire systems. I'm curious also from Paarth, like for example, like what are some of the tasks you feel, for example, the current development of large behavior model is already capable of delivering to create value in the business like scenarios?
Okay, I'm going to give you a quick answer to that because you asked it. I think it's a great question, and I will tell you that for grasping, we don't model physics. That turns out to be very hard. But for the placing, packing the boxes, we turns out that we use a very naive physics model. We just assume the boxes are parallel pipe heads and that they can't penetrate. And so we have a very, very simple simulator for those. And it turns out that works well for the packing problem, right? We're not trying to model the physics of contacts or even jumbling them. We're just assuming they arrive, they're static, you're picking them up, you can orient them and place them. But then being able to place them optimally is something that's very difficult as a geometric problem, but we just simulate that with simple physics. So that's a useful, to your point, there are some useful tasks like that I think can be tackled. And I agree with you. I'm not, that's a great point. I think that, again, I completely agree with that I think the way to get to fully general purpose is by bootstrapping with simple tasks that are actually economically viable, that people will pay for. And we can put those tasks, get them out and running, collect data from them, and then expand into adjacent tasks and adjacent skills. So I think that is a path to getting there. And so identifying what those are, I think I'm actually curious what the other panelists feel, or the rest of the audience are. What are the tasks that we can solve in the near future?
Yeah, I could talk from the TRI perspective. I think like the way I use I think the way we're using models in general is like mostly for like evaluation throughput. And from like the perspective of like working with Toyota or like putting something in a factory, I'm not like exactly Toyota facing, but I can imagine something like where we see a lot of success is like a lot of things like picking and placing and like testing generalization. And I think that's one where I really trust those models. I really trust our versions of like out of distribution, our like visuals and like how those transfer. And I think the general takeaways we get from like distribution shift is like something where like I really fully trust our models and how we're like doing that and how we're studying that in sim. For like more like dexterous tasks, that's like an open-ended question. And I think we still have a lot more work there to do to like really push on those models to like do things like using like tool use and stuff in sim, which we've done in the past, but like we haven't really explored as much with like scaling our simulation. So I think I think that's kind of how we've been using it, more like generally testing how these like models scale and like how like that may be useful for like Toyota.
So I can then ask follow-up questions for the entire panels. So for example, from like a Ken's example, so you are not simulating the interactions to the maximum fidelities. Some kind of approximation model seem to be sufficient. Like also for Paarth, like the model may not be perfect, but still it can provide you with some signals for evaluations. Then I'm just curious, like at what levels of abstractions, like should we actually represent the environments for us to do like a useful modeling? Specifically, if you are modeling deformable object or rigid object, their representation, their levels of abstraction may need to be different. Given a water bottle, if you want to grasp it or open the water bottle's cap, the representation may also need to be different. So even within the same task, if there's an object far away from you, you only have to know there's an object. As you're getting closer, you're starting to like focus on local geometry and detail of that object for you to grasp it. So depending on the object, depending on the task, even depending on different stages of the same task, the representation might need to be different. So for the whole panel, like how do you think about the levels of abstractions we should represent the environment?
There's a quote that I think is mistakenly attributed to Albert Einstein, which is that a model should be as simple as possible, but no simpler. I think that's approximately the right way of doing things in terms of our philosophy on choosing model classes. You know, we want to, we'd like to be able to have a system hypothesize multiple model classes and choose the one that fits its ultimate task. And so I definitely do feel like it needs to be sort of task-driven how you choose to model things. And it'd be great to have dynamically adjustable neural networks that were able to kind of handle multi-resolution, multi-fidelity kinds of queries.
Yeah, I think honestly you could, I mean, so there's actually quite a bit of work I've seen recently doing a lot of like these multi-resolution. As you get like closer to the object, it like is like increasing the physics level. I haven't really seen like the results that I want to see there, but they seem like there have been like people have definitely been exploring that. You can kind of think about it as like that as like an adjustable world model in some way. It's like, okay, I'm like my simulator is my model as I'm getting closer, you know, change the physics a little bit. I think as we like increase computation power in like the future, I don't think we'll have to worry about that nearly as much. We'll be able to capture a lot of these like nuanced dynamics, hopefully. If not, then like, yeah, this like these types of like adjustable representations seem like a good place to like be, where it's like they're fast and like also like capturing the relevant like details of the environment. And I think that's like definitely like super interesting as like an exploration. I think, yeah, that's all.
Yeah, I think so humans build abstractions of models to plan, and I think this is extremely powerful. That's why, you know, just committing on pixel generation or committing on 3D particles at particle level also maybe not the right thing to do. And I think choosing the right granularity is part of this test time thinking, right? It's like, oh, I'm looking for an apple, maybe I need to check on the fridge. Now, once you check on the fridge, I'm like, oh, maybe I should check the drawers. Oh, I see a red patch, maybe I need to focus on. So I see this as like the chain of thoughts that the robot would do to adjust its dynamics models on the fly, let's say, you know, from task to task. So this is also part of the exploration problem, let's say, exploring which abstraction to use.
Yeah, I think too.
Okay.
No, I agree. I agree with everything that's been
So I guess next question, I guess like I will gather keywords from Paarth, like he mentioned the word models. So currently there have been a lot of discussions on like word models. Obviously, different people's definitions of word models might be different. Some people will thinking about like video predictions or some other type of predictions. Like my definition has to be some kind of action conditions, like future predictions. Depending on the state might be using like different types of forms. So I'm curious from the panel, it's like if there's this type of word model, so what are some of the important characteristics you think is necessary for the model to be very, very useful for the downstream manipulation tasks? For example, does it have to be 3D? Does it have to be able to capture the semantics? So like, what are some of the characteristics that you hope this word model would have for it to be very useful?
Yes, everything. Yeah. It should probably be 3D. It should probably connect with 2D. It should have semantics, attributes, yeah, how things feel, you know, reaction connections with tactile sensing. You know, that would be ideal.
Yeah, I think just a multimodal world model sounds good. What I haven't really seen from any like world models right now out there is like how well they really generalize. And you need to be able to generalize in some semantic way. And that's like been one of the things I think that's holding back like some of that like the planning with the world models. I haven't really seen a lot of this like semantic generalization that's meaningful. And so I think that's just what's missing right now. And I think once you're able to like push in terms of like, yeah, push outside like these like your like distribution bounds in a semantically meaningful way, you'll like get like a lot more like power out of it. So like imagine like a simulator, you can move things from like the left side to the right side. With the world models, if you do that currently, it has no idea what the left side is. And it's like, okay, well, you need to be able to like have this common sense understanding how to like interpolate and extrapolate mostly. And I think once you get that, like it seems like a great place to be, kind of like having a playground. You can like reason in that space. You can do a lot of like really interesting stuff, like create like synthetic data in that space. But unless they can like generalize out of distribution, it's like not really buying it much.
So first of all, I do not know, but one thing that I really like is heterogeneity. I mean, in the past, we want to have this monolithic function that the actions in and state out and the state prediction comes out. Then the new version is okay. Let's just train the trajectory, the generative model over state action trajectories and so on. But if we look at the autonomous vehicles, they don't use this type of models. They use, let's say, thoughts that are, much like your teacher tells you pay attention now on the traffic light and pay attention to the stop sign and who is on the right and so on. So you have the model thinking, okay, let's see, I'm in the four-way intersection. Who came first? This guy. Okay, I need to wait for them. They don't have this monolithic pixel prediction model that predicts what's going to happen next. They focus on the relevant parts, and part of this instruction and the thoughts are exactly the level of abstraction. Who arrived first? Is this the red light or green? How close is to the front car and so on. So distilling these abstractions is part of building the world model as well. Now, of course, once you go to really fine-grained contact, yes, I totally agree with this type of representations. We care more like more dense representations there. But I'm kind of inspired of how the autonomous vehicles have managed to go around this problem.
Good. Okay, I would add, I really like what everyone said, but Katerina's point, I would say is something about attention. Being able to have a kind of spatial attention mechanism seems very important. It's very hard to introspect about this when you're manipulating things. What are you paying attention to? But it's clear that you're not just uniformly modeling the environment. You're focusing on critical parts of it. And I don't think we have good models of what that is. The other one I would add is models that they often struggle with deformation. That predictive models, tend to blur that out, and it's because deformation is just extremely difficult for all kinds of reasons. And then the last one, I want to also just argue for actually some models of non-determinism. Maybe you can say that's built in with world models because they're stochastic, but what I mean by this is that they can offer multiple outputs. And actually that is one thing that world model might be able to do, but actually being able to really pay attention to that, because especially when there's multimodal outputs, those can be very helpful and valuable. So I think, and especially, as we know, friction is non-deterministic, very difficult to predict. So having ways to capture alternative outputs, I think is really useful.
Yeah, those are great points. So my next question, I want to investigate a little bit more on the interplay between model and policy. So currently has been a lot of enthusiasms on this kind of large behavior model, vision, language, action models. And actually, to my surprise, over the past 2 years, it actually has been some kind of like a real progress along those directions. Although how far they have been going and whether they're enough, those are still questions. But this field has definitely been going quite a lot. So to me, I feel it is quite a loss by just using those data for imitation learning. So there's actually a lot of like dynamic informations or interaction information we could potentially harness from those large scale robot interaction data. So what is needed to train those robotic foundation model is action condition robot interaction data. So what is needed for us to identify or build some type of model of the environment is also action condition robot interaction data. So I'm just curious from the panel. So what do you see are some of the opportunities that we can combine the good old engineering and also our ideas of modeling of the environments with the developments of like a vision language action models.
Yeah, I mean, I actually really like the way we've currently set it up at TRI. I mean, I'm clearly biased. Like, I really like I think the controller is doing a lot of the work that like we're like not really exploring nearly as much, and I think that's like something we need to like actually think about and like actually maybe like benchmark. So I think the controller allowing us to like gather those like really dexterous demonstrations is like really important. I think there may be some more work to do there, like for a lot of corner cases and edge cases, like someone had asked me the question of like, hey, like it may like get into a singularity, and like if you have some sort of like MPC based control underneath it, which is model based, you could like maybe get around that. I mean, there's a lot of ways to do that. I think like, yeah, I think that's like a pretty like healthy API like difference between your policy and your like controller itself. Yeah, nothing controversial.
Yeah, I agree. Just look, so the question is that, look, we have all this data and we just use them to predict actions, and it sounds very weird, right? Yeah. So first of all, humans really don't predict actions, right? Because we're never teleoperated, and we always look and imitate and see what is the world state and try to achieve the same world state. This is the premise of visual imitation. So I think this is important. Now the question is, how do we get there? I mean, one thing that people do, because it's nice and universal, is they predict video pixels, but we already argued that, you know, this is not the right thing to do. I think one step in the right direction is what, you know, Gemini, the recent Gemini does, and Magma and so on, that they say, I'll predict the trajectory for the robot end effector. So I can imagine pushing this forward and saying, I predict the trajectory also for the object, and maybe also for this particular key point, I predict the trajectory. And maybe I can predict also a patch of exactly how the soup needs to look like, or maybe I can predict a soup video only for the interior of the casserole, because I know the casserole is going to stay there. So something more heterogeneous representation that combines motion and appearance on different parts of the scene selectively might be able to represent, you know, as build a stochastic model, because we do need multiple outputs, maybe able to, you know, capture exactly this scene evolution as opposed to just what is the action that we need to do.
I guess one more thing I would say is we're talking about things from the level of like representations. I think one thing I want to point out is, I mean, I personally, and I think maybe some of the community, I haven't seen any sort of like place where like some of this like scaling just like taps out. And so I think that's why I like currently have been like, yeah, let's just scale this up. I think there's definitely like a lot of places where like when things start to like reach some sort of limit, where you're like, okay, now we think back about these representations. And so really what I'm trying to say is like, there are representations that scale well, and like things like CompNets and stuff like that, where like, yeah, that scaled quite well. And I think we as a community just need to find what those representations are. I don't have the right answers, but I think something like, I could maybe see a place where we get to like, where 2D is like hitting a limit and you kind of have to really think about 3D. We're using something like key points. And that's where you like then start to think really hard about like which representations scale to then like move past that like bottleneck. And then maybe in like 30 years or 40 years, like that bottleneck goes away again. And I think it's going to be a cycle. And I think that's just kind of how we have to think about things. But the way I like have said it is just because I don't think we've really hit that limit with just like our current representations. And that's why I kind of said the answers I had.
Okay, I could add that I like that you mentioned key points, because I think that I hope this is relevant, but I think that there's something to be recognized about the potential of combining off-the-shelf VLMs with hybrid systems that use the VLMs to identify objects in scenes. And Katerina, you mentioned Gemini, which it seems as if Gemini is doing a fair amount of that. It's used a very sophisticated special VLM that's very good with spatial modeling, and again, it's able to do that. And I don't know all the details. I actually wish Google would come out with more about that. Maybe they have, but I think that if you could start to train, it seems like there's a lot of data that actually has been already out there, trains systems very well. There's lots of potential for increasing that to be able to do some semantic understanding of scenes, right? And so rather than training a VLA all over again to do that, right, there seems to be some huge advantage to combining them. And I know that's what people are doing to some degree by starting with a pre-trained VLA, but but I think that there's a lot of new engineering that can be done here. And maybe this comes back to the point. And here's just one example that we were training a system to do a particular task, and with VLA approach, we were giving examples, and it started working really nicely. But then if the scene were rotated ever so slightly, it started failing. And I said to my students, well, why don't we just rotate it into alignment, into the training example analytically, because we can detect the angle of it was off, and then we just rotate it back in and sort of treat it as if it's back in distribution. And my student said to me, well, I don't want to engineer it. I remember that. And I was thinking, wait a second, when did engineer it? When did that become a bad word? And so, but I think it's fine to do that. I don't know how others feel, but that to me was like, that seems like an obvious thing. It was such low hanging fruit, easy to rotate, right? We know transformation matrix trivial. And if you do that, then all of a sudden all your training examples can apply to all orientations of the scene. So why not? And I guess that I want to pose that back to the panel or to the audience.
Just one thing about I guess training versus building a business. So in order to encode business logic like safety or certain types of policies that you need to have your system perform, it's oftentimes easier to just write down some bits of logic, or have some business person tell an LLM to write code for some kind of logic, rather than training that logic to exist through essentially osmosis and through data. So I think there's a good kind of argument for having these models so that you can actually encode this kind of safety and business logic that will actually make you money, hopefully, while also getting good performance from learning.
Something on Ken's question, which I really like. So first of all, humans do mentally simulate, although they said that this experiment may have a little bit of a flaw. Like when the shape is unfamiliar, you ask them, these are the two versions, the same object, and they mentally rotate. But if the object is familiar, like a chair, they don't. So I see 3D perception, object detection, what Ken says, orientation, object by object orientation, all this traditional computer vision as the slow thinking, right? For when you are OOT, you need to detect every single object, estimate the orientation, maybe retrieve also another, manipulation you did, try to find the matching features, predict the trajectory, and in this way get data out of those traditional, what we call traditional model-based systems, so that you can distill them back to more end-to-end systems that even later, even with closed eyes and just a tactile thing, you can get your, key out of your pocket, or you can, place it or make a coffee, without really paying attention. So I really like this reorientation as a slow thinking.
Okay, those are fantastic conversations and discussions. So I think now it's time to open the panel to the audience. So who have any questions for the panel?
Hi, I have a question about kind of more philosophical question, like in our day and age, what do you think makes a good roboticist? Because we hear that engineering is super important, but we also see that I see a lot of frustration of roboticists looking for jobs these days, and all that companies are asking for is kind of experience in tuning models, and what does that tell us, like both for industry and academia, like what do we have to teach students, and is it what is like industry looking for, and is it correct what they're looking for? Yeah, I'm just interested in your thoughts on this question.
How much time do you have? I'm kidding. It's a very, very complex question, so I'm going to pass. Better answered over drinks, yeah.
I guess I can answer from a industry perspective, though I've also semi-recently graduated. But I think just so I have a background in controls, like a little of optimization, I think just being able to like actually think through problems in like fundamental. Be working on the robot, and I think just having like practical hands-on experience, both with like learning, but also like not learning experience or like not learning like methods is like just really, really important. And just being like, hey, like I'm looking at this robot. Why is this thing maybe like not working? Is it actually the policy? Is it the robot? Is it something else? And just like being like on the ground level and like thinking about these things and looking at that, like the practical experience of being a roboticist is like invaluable. And I think that's probably the like biggest takeaway. So I think spending a lot of time, don't just be like, hey, like Franca inverse kinematics, I'm just gonna put it in, hopefully it works. And you know, if it doesn't work, it's probably the inverse kinematic. Like, no. Like really think about some of the problems that like you're working on and why like there might be like other solutions, force control, things like that. All these things like I think will probably like go a long way.
Yeah, Ken, maybe you have better insights on this?
Sorry. Well, I think it's interesting. I really like.
You're muted again.
Yeah, I'm still muted. I'm still muted. You can't hear me. Am I muted? I think I'm not muted.
Oh yeah, now I think we can hear you.
Okay, all right. Well, you know, I think that having those sort of kind of what I'm advocating is that we keep alive this good old fashioned engineering. I'm not just doing it for sentimental reasons or, you know, sort of this sort of clinging on. You know, I think what in the sense of Rich Sutton, you know, like the old timers are clinging on to their old methods. You know, for I think, I mean, that would be very sad, maybe pathetic, and maybe that is what I'm doing. But I think that I'm doing it for a reason that it's actually, these are helpful, exactly as you guys are saying. I think that, you know, it's good to understand. I'm sort of thinking a little bit like Picasso, right? Picasso first learned how to paint, and he knew how to paint like a representational, he was a figurative painter. And then years later, he could then branch out into abstraction, right? And cubism. And he did that because he knew how to do the original thing, right? He knew the other way of doing it to make someone look like a person, right? And then he could take liberties with that because he understood the foundation. So maybe it's analogous. In other words, know how to build things in the old way and then build them in the new way. But you know, don't be dogmatic. I think that's my message is be flexible. I think that dogmatism is never really good. And I think there's a danger that there's some new generation that are coming out, and I see this in, again, my own students, I'm not blaming anyone, that are saying, you know, this is the way to go. This is, you know, this is the only way to go. And, you know, they're rejecting the old approaches. So I think it's really good to keep those around. That's my opinion.
I really think it's that's a very good point. I think it's really the ethos of engineering that we need to keep alive. And I think this kind of good old fashioned engineering is a way to teach that ethos, even though we may end up using new tools for that engineering.
Okay, thank you very much. Very interesting this panel. Rather than a question, I will try to answer your question about how you can try to combine simulation of this big data gap and the knowledge of we have inherited from physics and mathematics. Right? To start to answer the question, it's just I will attempt, right? Because it's very tough, right? We have to understand there is two kinds of manifolds. No, sorry. One is the sensory motor contingency, which was pointed out by scientists in the 70s who work in Paris in psychology. It was J.K. Malay, and called the sensory motor consequence. On the other hand, we have the sensory motor manifold. A sensory motor manifolds are a sort of Riemann mind, right? And all the attempts of robotics and engineering using data and trying all models are trying to represent what classic mechanics, right? Not relativistic, so classic mechanics, Newton mechanics, Hamiltonians can tell about a system, right? So then how we can combine this? On the one hand, you have this sensory motor contingents, which have been evolved through the evolution, right? By the persons, through the evolution, which doesn't, in this, there's no inversion of a matrix like a Kalman filter or a Riccati equation. There's other way, like have learning, right? Or stochastic gradient, right? So on the other hand, these manifolds you may get by using the sensory manifolds by physics or engineering, which leads to these Riemannian manifolds. They capture the structure of a non-Euclidean space, which are called manifold of Klein or studied in this special Euclidean group. So that's the only one you can capture. So now how we can combine? Does it just? I am not sure, right? I'm trying to do an effort. If you use, for instance, variational autoencode, you in the latent space, you carve this spectral manifold. Now, by data, this can tell us, use the data, okay, use this data to recreate this manifold for a certain purpose. Now, looking on this manifold, you can use the minimization of geodesics, which takes into account optimal paths and minimization for area. So that's the way you are combined. That's I'm trying first.
Yeah, I think this makes a lot of sense. There was also a very cool paper that was training latent spaces so that linear dynamics or simple dynamics could work there. And I'm very happy to discuss this after the panel.
Sorry, I want to comment also. There is side since 10 years, physicists have been working with the physics information neural network, trying to decompile a dynamic model of a system. It's important to look at.
Thank you very much.
Okay, so I think this is the end of today's panel. So thank you, everyone. I thank you for all the panelists. It's a great conversation.
Thank you. Thank you for organizing. Thanks, everybody.
Thank you,
I'll be down there tomorrow. All right.
So yeah, so now entering the final parts of today's workshop, which is awards. So like there's a committee for this workshop, and this committee selected like one best paper finalist and one best paper awards. And the best paper finalist goes to learning the contact manifold for accurate post estimation during pegging hole insertion of complex geometries by Abhay, like Ome, Meyer, Danush, like Varma, and Satyajit.
That's fine.
No. Okay.
Congratulations. Thanks so much.
And next is the best paper awards. The best paper award goes to adaptive compliance policies, learning approximate compliance for diffusion guided control by Yifan, Zheyi, Chen, Eric, Navi, Xiyuan, Benjamin, and Xuan. Congratulations.
Thanks so much.